Good morning and welcome to Science for Dialysis. Today we are going to talk about a very interesting issue, big data technologies and how big data can help in the field of medicine. As you know, currently the healthcare system produces lots of information, different kinds of information such as images, clinical reports, and if we are able to put all this information together, we can improve the efficiency and the quality of healthcare delivery. From my point of view, big data is the paradigm of evidence-based medicine. And if we are able to use it correctly, to use these technologies properly, we can improve patient care, but also the prevention, the diagnosis, and the treatment of diseases, in our case, renal impairment. To achieve these goals, it's very important that all stakeholders work together and commit. And when I talk about stakeholders, I mean doctors, I mean university, private industry, research centers, administration, etc. Promoting big data research is important because it allows to go forward personalized medicine and personalized therapies. In this regard, on behalf of Hospital de Bellvitge, I would like to thank the presence here today with us of Hospital Bartaulí, the Intelligent Data Science and Artificial Intelligence Research Center de la Universitat Politècnica de Catalunya, and the Barcelona Supercomputing Center to share their knowledge with us. I would also like to note that the health system has a pending issue with physicians, because physicians should have the possibility to do research without this implies an overload of work. That is the situation, the real situation of the physician currently. And this is a point to work on. And finally, I'm sure this will be a very successful meeting, and just say, please enjoy the meeting. Thank you very much.
Buenos días y bienvenidos otra vez a esta nueva reunión de Science for Dialysis. Es la cuarta edición. Los organizadores, el doctor Hueso y el profesor Bellido, me han pedido que haga una breve introducción. Mi nombre es Josep María Cruzado y soy el jefe de servicio del servicio de nefrología del Hospital de Bellvitge. Y en primer lugar, daros la bienvenida a esta iniciativa, para hablar de estos temas tecnológicos, sobre todo alrededor de Big Data y su utilidad en el campo concreto de la diálisis. Y un poco a modo de introducción me gustaría mencionar algunos conceptos. La enfermedad renal crónica es una enfermedad muy prevalente. Aproximadamente el 15% de la población tiene algún grado de insuficiencia renal. Es cierto que en esta sesión va a estar muy focalizada al ámbito de la diálisis, pero la diálisis como tal y el trasplante, que serían las dos técnicas de tratamiento renal sustitutivo, es decir, cuando falla, cuando se pierde completamente la función del riñón, disponemos del trasplante renal y de la diálisis como herramientas, como tratamientos para que los pacientes puedan continuar con sus vidas. Pero la gran mayoría de los pacientes con enfermedad renal crónica no van a necesitar diálisis. Estamos hablando de que si el 15% tiene cierto grado de insuficiencia renal, luego menos del 1% van a necesitar ese tratamiento renal sustitutivo. Pero en cambio, toda esta gran población de enfermos con insuficiencia renal sí que van a estar o van a tener complicaciones y la propia enfermedad renal representa un enorme factor de riesgo para morir precipitadamente. Es decir, hay toda una investigación que debemos realizar alrededor de la insuficiencia renal para reducir el impacto que esa insuficiencia renal tiene en los pacientes y para también minimizar el riesgo de acabar necesitando diálisis o un trasplante renal. Todo esto lo hacemos en colaboración, obviamente, con muchos profesionales de la primaria, profesionales de otros centros hospitalarios, y todos en conjunto trabajamos con la filosofía principal de que el paciente esté lo mejor tratado posible y que ese paciente no acabe necesitando esta diálisis o ese trasplante. Pero desafortunadamente, a pesar de este trabajo en red que realizamos los nefrólogos con otros profesionales del mundo de la salud, profesionales de primaria, profesionales de enfermería, etcétera, los pacientes acaban necesitando ese tratamiento renal sustitutivo. Pues bien, lo que desde el Hospital de Bellvitge estamos trabajando es para que centrar la toma de decisiones alrededor de cuál es la mejor opción de tratamiento renal sustitutivo, la tome fundamentalmente en paciente en función de sus características y necesidades. Para ello hay que trabajar, hay que visionar el futuro y hemos conseguido con el apoyo de nuestro centro y de las autoridades sanitarias, pues disponer de unas nuevas instalaciones, si ponéis el vídeo por favor, de unas nuevas instalaciones para dar solución a este concepto de que el paciente acabe decidiendo qué tipo de tratamiento le conviene más. Dentro de esta toma de decisiones tenemos el trasplante antes de llegar a la diálisis, fundamentalmente el trasplante de vivo, pero también las diferentes opciones de diálisis, que las podríamos agrupar en diálisis domiciliaria, es decir, el paciente se la hace en casa, o diálisis en un centro. En estas instalaciones lo que hacemos simplemente es esto, es decir, el paciente entra por la puerta y a partir de ahí decide cuál es su tratamiento. Y una vez decidido nos dedicamos a darle el mejor tratamiento posible, ya sea la diálisis peritoneal o la hemodiálisis en su domicilio, a través de nuestro equipo de médicos y sobre todo, ¿no?, y es fundamental la enfermería. Y si el paciente decide que su mejor tratamiento es una diálisis en el hospital, pues disponemos de unas instalaciones con todas las garantías para ofrecerle el mejor tratamiento. Este entorno y esta colaboración con nuestros partners del mundo de la diálisis nos va a permitir innovar, entre otras cosas, innovar en tecnología, innovar en manejo de la información. Durante los tratamientos de diálisis se genera muchísima información y esa información es susceptible de ser procesada y tratada, y un poco en este sentido creo que es muy importante las iniciativas como las de el doctor Hueso y el profesor Bellido para poder potenciar y generar conocimiento alrededor de estas nuevas tecnologías y nuevos análisis de los datos. Nada, muchas gracias y espero que disfruten de la sesión.
Okay. Welcome to the new Science for Dialysis forum. This year is devoted to big and complex data analysis and personalized medicine. Our title summarizes our intentions: data modeling and representations, algorithms, and hardware news. I'm Miguel Hueso from the Bellvitge Dialysis Unit, and I will be involved in this adventure with some friends, Alfredo Bellido from the UPC and Karina Gibert, and two enlightening research Josep Piveas from the Partaulí and Alfonso Valencia from the Supercomputing Center. He will be connected in Madrid. Healthcare system and, of course, nephrology involve very complex structures and high-dimensional interactions among multiple factors where diseases are difficult to model and in their globality. Data analysis are too often based on techniques designed for linear phenomena, which should not be applied to systems characterized by non-linearity, constant change, fragmented but highly interconnected, and time-dependent. How to model this complexity? Data production is currently on an exponential growth curve, and it seems endless. The global information network is now growing at about 205,000 gigas by second, which represents a constant barrage of structured and structured data. According to the IDC projections, 80% of world data will be unstructured in 2025, but we are also dealing with non-linear variables. Omics studies are developing at a fast rate and each time are cheaper. On the screen, we can see an impressive view of the human interactome and RNA sequence data from single cells. How can we model this complexity? Classical modeling based on algebraic formalism cannot capture the whole structure and poor results are obtained. Thus, new approaches are needed. Complex data need additional work to prepare and model the data before the analysis. Our aim is to analyze and to identify risk population and patients to treat. This is an example about the difficulty to identify some risk population. Here in the screen, we could see two populations that are very easy to study because they are linear, but they are also non-linear, and some mathematical approach we need to explore this data. Thus, we have the pieces and we have to build the puzzle. How do you know that you put each pieces in the right place? And in addition, how can you be sure that you have ordered the pieces correctly? How you can test the quality of your results? Here, the pieces could give this 16 chapel, or maybe you have forced your model and obtained some picture that it's maybe a mixture of different populations. So some new approaches are defending the advantage to incorporate prior expert knowledge into the analysis. Classical data analysis methods guided by prior experts' knowledge should allow a better modeling of this phenomena and improve the quality of the results. Then a question emerged: how to include expert knowledge into the analysis? How to identify this expert knowledge? Thus, the objective of our data analysis is focus in personalized medicine. That means correct diagnosis and precise treatment at the right moment. Thus, we have to deal with several challenges. Here we are going to discuss two of them: modeling algorithms, optimization, and knowledge extraction from predictive models, an application of machine learning and deep learning techniques to nephrology by Josep Piveas from the Partaulí. And in addition, we are talking about high performance computing and hardware innovation for big data with Alfonso Valencia from the Barcelona Supercomputing Center. He will be online from Madrid. So I hope that you enjoy this presentation. And now Alfredo Bellido from the UPC is going to give some news about the EDI and the UPC, what they are working now. So, Alfredo. Thank you, Neil.
Well, hello everybody. And first of all, thank you for being here. where here is a Brave New World type of format, in which we are streaming through YouTube, but maybe you're joining us through the recording of the session. Let me first, please, thank Dr. Hueso for being the engine behind the celebration of this workshop, Science for Dialysis, in which we are, believe it or not, in the 4th edition. We truly hope that the 5th edition will be again back person to person, because it's always nice to interact with people in other ways other than a YouTube channel or something like that. Let me also thank Hospital Belviche for hosting this event through the years, to Dr. Evelyn Shaw, Deputy Head of its patient hospitalization and patient management. I think that's the official title. And Dr. Josep Maria Cruzado from Nephrology for their kind introduction. Okay, let's say that I am the artificial intelligence part of this event. I do belong. I'm an associate professor at UPC, Barcelona Tech, and I belong to the. I've been doing research in artificial intelligence as applied to medicine for a long time now, but I do belong to the Intelligent Data Science and Artificial Intelligence Research Center, IDEAI UPC, which, as you can see in your screens, was created only a few years ago, right? 2017. In fact, we've been active only for a couple of years, maybe not much more, even though formally we've been around for a few more years. And you might think, well, okay, maybe UPC has woken up to the reality of artificial intelligence suddenly, and they have created this artificial research center. Well, this is not the case. As I said, I've been around artificial intelligence for medicine and health for a long while. In fact, I've been working on that for 25 years now. And at the UPC, at least for 18 of those 25 years. And indeed, artificial intelligence has been a reality in research, in academia, and to some extent outside the academia for a long, long time, right? Artificial intelligence is by no means a new concept. It only really took off in the 1980s. And even when I joined the world of artificial intelligence in the late 1990s, it was still somehow a kind of novelty, right? It was still considered as a kind of new kid in the block of computer science, mostly because artificial intelligence draws from mathematics, especially from the world of statistics. It also draws heavily from the world of computer science. So at the UPC, as you can imagine, there were already quite a few people working on artificial intelligence. Actually, there were many more than I even knew that were working in artificial intelligence. The reason we created IDEAI a few years ago, it's for me a sign of the times. Suddenly, quite suddenly, from an academic point of view or a research evolution point of view, artificial intelligence has become something different, something you could say special, especially in the sense that suddenly society is aware of what we are doing. We did realize a few years ago that many people from the outside, even people from the inside, were trying to contact artificial intelligence researchers, but they didn't know where was the door at the UPC for people in artificial intelligence. So basically they search for people, they Google us, and well, when they found someone who was apparently interesting or related to whatever they were looking for, they contacted us, all right? Which is fine. But the point is that we realized that there were too many of those people from industry, from academia, etc. And we didn't have a single door of entrance to artificial intelligence at UPC. So basically, EDI is a virtual research center, is the coalition, is the network of all or almost all people doing artificial intelligence in its many uh, shades at the UPC. Okay. Uh, Suddenly we have a single door of entrance, for anything related to artificial intelligence in our university, which really, even though it might seem like trivial to some extent, but it has changed completely the way we approach this field of research within academia. In fact, from the very beginning, we realized that because the diversity of skills and goals and types of applications people doing artificial intelligence at UPC were dealing with, we needed to make a structure out of EDI by areas of research. So for instance, we have a section devoted to Industry 4.0, which is to say, industry at the forefront of technology applications. We had applications in economy, an area devoted to economy, to education, to innovation, to efficient resources, involving, for instance, environmental modeling, an area in which UPC has been at the forefront for a long while, but also health, wellness, and inclusion. And in fact, I'm the co-coordinator, together with Professor Dr. Karina Gibert, of the health, wellness, and inclusion area of EDI. And even the title reflects, let's say, the diversity of things you can deal with when talking about biomedicine, artificial intelligence as applied to biomedicine. I mean, one part of it is health as such, the more, let's say, traditional medical applications, but also wellness and inclusion are part of it. And there are lots of people working on, for instance, robotics as applied to inclusion in medicine, which have a very strong research record on that area for a long time, which are also part of this section. And as you can see at the bottom of the slide, there are quite a few individual research groups involved. Okay, and they cover almost all the aspects, all the possible aspects of artificial intelligence, applied to image, applied to language, applied to vision, traditional machine learning, the whole caboodle, really. In fact, you might say that it's even though it's virtual, but it's a big center. I mean, right now we are almost 70 senior researchers, together with the groups involved, together with the PhD students working in the area, master's thesis students, etc. A whole artificial ecosystem within UPC. And many of these, perhaps surprisingly, perhaps not, work, or at least do part of their work in biomedical data analysis, using, as I said, different types of artificial intelligence. In fact, all these areas, from a strategical point of view, try to coalesce, try to work together, even though each of them obviously has its own targets. But we are trying to coalesce in the sense that we are presenting ourselves as a united front with institutions and with industry. And this is a key part, in my opinion. If we want to have an influence, a reasonably strong influence, for instance, in government and governance, if we want to go to the institutions, not just to, I know, Generalitat de Catalunya, but also at the state level or even at the local level, municipalities, we really need to present ourselves as a kind of united front. It's, you could say it's a matter of numbers in the end. I mean, it's not just a few researchers or a small research group trying to knock the doors of the institutions. It's already a bigger research center that is providing, multiple solutions to multiple problems. Also, although I haven't mentioned it before, and as you can see in the slide, we have, or we try to have, the concept of ethics in the center of it all, as a core value. And you might wonder why. And the point is, and this is perhaps curious, in artificial intelligence, the concept of ethics has only come to the fore very recently. Artificial intelligence as an in silico proposal to simulate natural biological intelligence. Well, surprisingly, artificial intelligence for a long, long while has never considered this aspect of natural intelligence, which is values, ethics, call it morals, whatever. Ethical aspects of artificial intelligence have never been part of artificial intelligence from inception. That's a reality. Okay. Only in the last few years, the artificial intelligence community has realized that we cannot ignore that easy. Why? And this is for me the important thing, because suddenly we are not just in the academic realm, in the research realm. We are having a strong, really, really strong and increasingly strong impact on society at large. If artificial intelligence is to have an impact at large in society, we cannot ignore ethics and the ethics involved in the application of artificial intelligence any longer. It's that simple and that complex. And maybe some of you are aware that only recently, at an institutional level, at the governance level, people are beginning to, or governments are beginning to consider regulations on artificial intelligence. Okay, only a week ago, this last week, the European Community released the first draft of regulations on artificial intelligence as applied to anything in the realm of citizenship. In fact, even a diagonal reading of this first proposal reveals that it's the GDPR as applied to artificial intelligence. Roughly. I mean, this is obviously a gross simplification, but it's basically that. And these regulations establish, a few areas which are supposed to be high risk in terms of the implementation of artificial intelligence. And we really need to explore the impact of things such as that in health and medicine. Okay, whatever we do using artificial intelligence in health and medicine now has to go through these type of regulatory filters. And that's, again, another example of how artificial intelligence and its impact on society cannot be separated any longer. I mean, if we really want to apply artificial intelligence in any way in the health sector, in biomedical applications, we really need to address these issues, which, by the way, the medical community have addressed forever, through ethics committees, or, even by its own inception. Ethics, it's at the core of medicine. Well, now we need ethics also at the core of artificial intelligence, and especially when artificial intelligence is applied to medicine. Okay, this is the way we describe our strategy in health, wellness, and inclusion as part of EDI. Artificial intelligence to support the most updated, the state-of-the-art concepts of health and related areas. And even in this description that you can find at the EDI website in UPC, we, from the very beginning, from the very first sentence, we talk about personalized medicine. New approaches in health evolve towards personalized medicine. Patient-centered medicine and wellness and inclusion are becoming important fields on top of the traditional approaches, where the main focus was symptomatic treatment. Okay, ICT technologies and artificial intelligence are recognized as, key tools to address personalized medicine. Okay, this is an important thing because, to be honest with you, and this will be a matter to discuss over this session, it's not that clear, how artificial intelligence related to big data is to be fully linked with the concept of personalized medicine and evidence-based medicine. Okay, that relation is a relation on the making. I mean, even myself, that I've been working for a long while in this sort of area, I still don't have a kind of clean cut uh, um, a scenario in my mind of how can we realize that for sure. Also, and this will be almost the last thing I will mention about EDI, and it's something I think it has to be said. Artificial intelligence, it's an umbrella term. It covers lots of things that are not necessarily that interrelated. Okay, they have a history of togetherness, a history as a common thing, but it's an area in evolution, right? So there are quite a lot of things that can be called artificial intelligence, even though, well, I mean, they are only loosely related, and some of them we have dropped them in this slide. From distributed AI and normative systems, computer vision, machine learning, natural language processing, intelligent data science, soft computing, computational linguistics, intelligent decision support systems. I mean, and there are probably quite another few terms that we might have dropped, like computational intelligence or data science as such. Obviously, they don't mean the same thing. I mean, each of them has its own area of expertise, its own approach, but all of them, belong to this kind of big family of artificial intelligence. But that's something I would like to insist, because what we project towards society, it's artificial intelligence as a kind of established science. It is not in my opinion, at least. It's at the best a science on the making. Some people argue that it's a subfield of computer science. I might argue that it's not necessarily just that, because it has strong links to biology, because of this idea of trying to imitate natural intelligence. There are strong links to mathematics and statistics and even other areas, which are not necessarily even ICT related. Okay. For me, in the end, that's not that important. Okay. I think we can live with that variety. We can live with all those approaches working together towards set goals. And the important thing is that in medicine and health, those set goals, are very wide, are very broad. As you can see, we reflect here at the EDI website that we have 20 plus years of experience in health in many areas: oncology, nephrology, as is the case, ophthalmology, epidemics, intellectual disability, neurodegenerative diseases, mental health, integrated care, inclusion. And again, this doesn't even cover all we do, right? We could talk about mobile health. We could talk about critical care. Probably, and this is again an important message, in my opinion, any area of health and medicine in which data are generated and available for research, that's an area in which artificial intelligence and data science can be applied. It's as simple as that. We need data, not even necessarily big data. Many of the problems I have addressed in medical applications are not big data at all. Actually, quite the opposite, are small data problems. And those are important in biomedical applications as well. So although there is, again, this other buzzword, big data, around, which is fine, but not everything in medicine is about big data. Okay. And with that, well, I hope I've given you a kind of at least first impression of what we do from EDI and from the UPC in relation to health. But I insist, I mean, it's only in the last 3 years that we have coalesced in a research area such as this, formally within the university. And for me, again, this is a sign of the times. We really need to have a group within a fully technical university such as UPC, only to consider the potential applications of data science and artificial intelligence in the area. Only this way we can sensibly approach institutions such as the Catalan health system, or even an individual hospital like Hospital Belviche, or whichever other hospital in the metropolitan area and around, with which many of those we have a strong relation, with Valdebron, with Hospital Clinic, etc., Parc d'Aulí, you name it. Probably, I mean, at this point, we have already collaborations with probably almost all hospitals in the Catalan area. But yeah, that's the key. I mean, we need to present ourselves as an academic front, to offer solutions to people in the medical area. And without further ado, I think we can introduce the first main speaker of the day. Yeah.
Now, going to explain his experience in this new area that they have built in Partauli. So we are expecting.
Thank you very much, Miquel. Thank you, Alfredo. I'm going to open the presentation. This one, I think. Perfect. Well, first of all, I would like to give you the congratulations for this fantastic meeting. It's really fantastic because there is nothing now in the market. You're pioneers in this. And really, we need to encourage the people to work in this field. And we need this kind of symposium. It's very important because I, as clinician, recognize that we need really this kind of forum. As Alfredo says, have been a very long winter in artificial intelligence during these years, and we have waiting until the capacity of the computers now and the price of the computers be able to work in this. And this is the secret that the expansion, the spread of the artificial intelligence by engineers reach nephrology. I want to congratulate you also by an important issue. You have joined here three kind of speakers. One, the clinician like me, that I'm going to try to give you the message as clinician that do we really need when we work in artificial intelligence. I would like to put you in my skin. Second, people like Alfredo and exploring artificial intelligence in software, in all related with the creation of algorithms and so on. And the third point, Alfonso Valencia, that's exploring computing systems in hardware, all related with computer centers and all the infrastructure we need in order to make big calculations. So here we have the forum in order to give the opportunity to the audience to speak a lot of topics, but for the different perspectives. Okay, in this context, my aim is to try to give you the perspective of a clinician. Lily, some of you that know me very well, I came from the field of the evidence-based medicine. I like informatics, and some years ago I started to work in this field. And really, I would like to transmit you the feeling of a clinician, feeling how the field of knowledge is changing. For this reason, I would like to, keeping with the idea of the organizers, give you the perspective of the application of machine learning techniques in nephrology, or mainly in chronic kidney diseases. Well, the different steps of my talk, I'm going to go through, all related first with the different steps from the evidence-based medicine to data-driven medicine. For after going through what should a clinician know about artificial intelligence, and after, from a practical point of view, the modeling algorithm optimization and knowledge extraction from predictive models. And finally, give you the perspective of how it works artificial intelligence in nephrology, and why not to speak about our experience. Well, what's evidence-based medicine? Evidence-based medicine is the mixture between the clinical expertise, the best evidence that we can get from the literature, from the experiments, from the trials, and the patient values. This is quite good. This is how we work today. But this is quite good from some points of view, but from other points of view, have the problem of the bias of the human being. In fact, when we review how it works, the evidence-based medicine, we see that, as you know very well, that we can go the route of the methodology, depending where we're studying, until reach RCT, randomized clinical trials, in order to get the best way, the best evidence of the works. But if we go through the filtered information of the interpretation of all the different works, we depend on the quality of the evidence. And this is crucial because we realize that we need in any work that we do to do the critical evaluation, the critical appraisal of the studies. This is crucial. Why? Because finally, we always must know in what extent we can trust in anything that we read, because can be a lot of bias. In fact, a lot of RCTs decrease the capacity of give some advice to the clinicians depending of the quality of the evidence, depending of its quality of evidence that perhaps is not quite good. And in a reversal way, the observational studies can grow its capacity of give some advice depending of its high quality. And the other point that is not writing here is that if we need evidence in some fields, if there isn't anybody that wants to have any kind of interest in this field, we are not have any kind of evidence. And this is really a problem. For this reason, when we work in evidence-based medicine, the first step is know what are our aims, what is the field of interest. Second, we should train the people because it's not easy to work in evidence-based medicine. The people confused between the evidence-based medicine and experience-based medicine. This is a critical problem. And if we have this problem in evidence-based medicine, imagine in artificial intelligence. And the rest of the points go through a roadmap depending on formulation of clinical question, literary research, reviewed evidence synthesis, recommendations, and so on. A different steps that makes that sometimes, and it's curious, the same literature, but with the same patients, with the same problems, depending who interpreted the literature can have different results. I'm going to put you an example. I work in the field of dialysis related with the vascular dialysis. The vascular dialysis are the connections between the human being and the machine. And that had been a lot of guidelines some years ago. And now in the last years, we have different guidelines, the Spanish guidelines, the European Society of Vascular Surgery guidelines, the EDTA, the European Society of Nephrology guidelines, and the American guidelines. These guidelines are made with the same literature, with the same patients, and with the same environment in order to interpret the literature by different experts. In fact, I personally am involved in two of these guidelines, European guidelines and Spanish guidelines, and it's a pity to recognize that the same guidelines doesn't say the same. And why is that? Because if we in evidence-based medicine, we have to mainly make a recommendation as we depend on the best evidence, the clinical expertise, and the values and circumstances of the patient, then although we have some systematic reviewers that make, from a technical point of view, the review, we depend on the clinical expertise that interpret the review. Can be people of different countries, different environments, different specialties, surgeons, nephrologists, interventional radiologists, and finally, the patient. So we have a balance between all of these circumstances. And this is the reason why, or because probably we have different results. For this, in a context where the industry 4.0 have arrived and where we have big data, any kind of data can be analyzed. We have the cloud computing, the computer distribution systems where we can immediately analyze this data. And we have the IoT, Internet of Things, where the artificial intelligence systems can embed it in the big data and the cloud computing. Then we can have a completely different approach. And this is the question of the paradigm shift. This is an important aim in order perhaps to discuss afterwards. In the evidence-based medicines, we have a lot of advantage, but the problem is the human being is open to create some kind of bias, as you have seen before. And in artificial intelligence, on the other hand, sure, with a lot of training, with a lot of work by engineers, methodologies, faculty, and so on, we can create otherwise precise, personalized recommendations that could not come from population-based medicine studies. So These potential biases of evidence-based medicines can be overcome with data-driven medicine. And this is the point of the AI algorithms that can give for us this in this. Okay, this is the strength of this kind of algorithms can give in this context a lot of help. Well, are we today in this scenario? We have a fantastic doctor with a lot of information in front of his eyes and with the possibility to make the application immediately artificial intelligence in the mobiles, in hospitals, computers, and so on, or not? An open question. Second point, then in this context, in a context where there is no clinician, there is no people training artificial intelligence, and the most of the people like you, they are seeing this kind of symposium, an open question is very important to answer. What should a clinician know about artificial intelligence? And I would like to put yourselves in my skin. When I started with this, I realized I work in dialysis. I work with colleagues of make surgical procedures, follow up with a lot of data in nephrology, and all related with imaging. All this data is centered in one patient. And this patient produces a lot of data every minute in the critical situations. And every patient is joined to a network of patients in one center. And in one center is joined to other centers. So here we're close to big data. And all this data should be analyzed. Then in this context where we have a lot of centers with a lot of information connected in a network that is able to be analyzed, then we have the first point to understand what is big data and how can I analyze the big data. Well, the definition of big data is really easy to understand. It's all the data that I introduce in a computer in my table. I press the button, enter, and doesn't work. That's the definition of big data. Alfredo, if I'm wrong, please you correct me. But if I can work if in a computer, that's not big data. In fact, we usually the clinicians speak about big data when we speak about further than petals and so on. But in any case, the definition of big data more than the size is really that I have not only with a lot of volume, but a lot of value for my aims, variability, variety, different kind of structure of the data, and structure and so on, and mainly the velocity. Immediately, I can have the results. But how can I analyze all this data? Well, here you have all kind of analysis I can do. We are used to work in statistics, but really our aim is to recognize patterns. And for these, statistics have some kind of limitations. For this reason, with the data mining, that is preparation of data, we can use the artificial intelligence. And in the heart of artificial intelligence is the machine learning. So the first point is to recognize big data or the possibility of analyze massive data. And the second point, who is going to analyze this data? There are four kinds of professionals. One, the data analyst, the classical colleague that works in statistics. Second, the data scientist, that is the usual colleague that works in machine learning and all the language related to machine learning in order to have results to our aims. The data engineer, that is the colleague that works with all the previous knowledge, but also with software, hardware, and so on, and mainly is able to work in huge data warehouses. And the data architect that have knowledge not only of the previous issues, but also security connections, communication protocols, data warehouse, and all related with the basic technology that underpins everything that we touch in informatics. So the second step should be know that we have to go through different stages or phases in big data. First, when we are going to write an article in medicine, the only thing we have to do is have our aims, methodology, and statistician to help us. And perhaps like as important point that you can speak before and after is the order of the authors in the paper. But what is the translation of this? The translation of this is that we have to create not aims, but a strategic roadmap. Is all the contents, all the different issues that we have to contemplate in this roadmap. Second, the business model. This is crazy for a clinician, but think that in a paper, it's going to be published, sometimes, or the majority of the times, the paper dies there. But in the technology of artificial intelligence, finally, my aim is to create an algorithm, a model that is going to be introduced in a computer by interface, and this is going to put in the market. So if I don't create the business model in order to put it in the market through this roadmap, I'm going to lose not only time, but money. Necessary of resources, the specific roles and responsibilities, architecture, all related with tools and technologies, data governance and standards, executive support, organizational adoption, analytics and reports. A more important point, lastly, is the understanding and interpretation of our results. So if we don't think in another way like this difference of the classical statistics, I'm going to be losing in this roadmap. Next step, how to generate artificial intelligence project in health. We are speaking about the project just now, specifically the project, not governance. Well, first, the question. Second, data. Three, the team. So I have to learn to work with engineers, and this is crucial because the people that's going to be on board depends its capacity of collaboration, the success of the project. I know how it works, the hardware and software. I have to demonstrate the value of the project because the manager of the grant is going to pay this. So if there is no KPIs or some indicator that speaks about my efficiency, I'm not going to get the results. Define the usefulness, the product development, standard validation, and so on. And the more important point is not really the standard validation, is that I have to produce a software in order to be commercialized. This is a new topic for the clinicians. Well, what about ethics? Alfredo gives just a few minutes ago some words about ethics. This is a crucial issue. In the ethics committees of a hospital, now we have to have engineers incorporated in our teams. But the clinicians, so we should know also something about ethics, artificial intelligence. When we work in ethics committee, we realize that sometimes it's difficult to interpret how to evaluate these kind of projects because there are three kinds of ethics here. The ethics that depends of the data. That means what about the security, the law related with the privacy and so on. The ethics of intelligence. Second, this is related with my algorithm, how it works. It's going to be good or bad for the patient, have some risk. And finally, the ethics of the practice, all related with the different environment of artificial intelligence. Because finally, although we, the doctors, are going to be responsible or make the signature of the advising to the patient, that this advice is going to be given by a machine. A very smart machine, but the responsibility is mine. How we're going to journal this because this is going to go to the patient. That always is the center of our decision score. Well, in this context, once you have explained your word about the main characteristics of how to create a project, the different steps to a roadmap to create the environment of artificial intelligence and the new professionals, in data science, we have to understand very well this point. Probably is one of the more important slides of this work. It's easy to understand what's computer science, all related with the computers. This is iron, that informatics says iron. Second, what about the experts of mathematics? This is the people that create the algorithms. After the data scientists, data engineers work on. And after we have here, where are the clinicians, the experts in the subjects that we know all related in this case of chronic disease. If we go to the central points between these two areas, the computer science and the experts, we have the traditional software. If we go in the middle of mathematics and the expertise, we have the traditional research. And the machine learning then is in the middle of the computer science and mathematics. So we would like to go for the red dot, that is to look for the people that have the knowledge of machine learning, of the software, of the traditional research, and the expertise. How this is called? The unicorn. Have you seen anywhere an unicorn? No, doesn't exist. So the point really is this. Have you seen the movie Star Wars, the Mos Eisley bar? Here you have the multidisciplinary team. Because really, as the unicorn doesn't exist, we have to create the best environment, to create the relationship of the different actors of this scenario to create the best model. Here is facile to recognize the mathematician, the engineers, the data science, and so on. And here, the clinician that doesn't understand nothing today. So as the unicorn doesn't exist, we have to create this environment, at least to sit in the same table. Well, once we have give you the main approach in order to understand in a better way how it works in this scenario, let's go now how to extract knowledge in artificial intelligence to create predictive models. Well, first point, in machine learning, the first point is to recognize what is my aim, to specify the problem, really. More than the aim, the problem to be solved. We have to prepare the data. Probably we are going to spend the most of the time preparing the data, choose the learning method, apply the learning method, evaluate the methods and results, optimization, and report the results. This is easy to understand, but here we depend on the people that it was in the previous table. Well, for this, the first point, that is the data, we need all the, we have all the scenario of the data of the hospital, pharmacy, lab, radiology, all related with the free text and so on. And this is to understand that we can work this in a system from the clinical point of view, point of care, statistics, research, but really that we need is work in data with artificial intelligence. Then the first content that came from one of the first slides is the data mining. We have to recognize what kind of data I have in my hands, because it can be structured or unstructured. Structured is all the kind of data I can put in files or rows in a table. Unstructured is the data that I cannot put in a table. So it can be free text, can be image, audio, video, and so on. And there is semi-structured data that are some kind of data that depend on labels, for instance, internet data, and so on. So in this context, I have to recognize that my data can be diagnosis, medication, lab, demographics, so data that came from sensors. I have to order very well this data, because the clinician is who is the responsibility to select this data, to interpret what to do with the machines. In fact, the engineers are able to create a fantastic rules or use fantastic tools in order to make interpolation with our missing data. But how do we interpret that this data is missing or not in the balance? Depends on the clinician. The other point is that we have to work, we are able to work with unstructured data, or depends on the free stage, imaging, and so on. And this field really is wonderful for the clinicians. So the combination of this is this roadmap. This is to understand. I have the raw data, I think how to go to different steps, and these different steps that go through all related with the preparation of the data, transformation of the data, extract patterns, goes to one of the more hardest phases in data managing, that is already with the preprocessing. That is means to clean the data, to transform the data, to reduce the data in order to adapt the data in the better way that algorithms can eat this data to finally create the algorithm in order to extract the patterns, and after to extract the knowledge to take decisions. So this is one. So in this context, we are going to grow really through the next step, that is to create the algorithm. This is one of the more important slides of this talk. Well, until now, when I speak about all related with the traditional programming, I'm speaking about that I get the data. This data usually includes the outcomes. For instance, I know that this patient, this group of patients, I want to know if they die, if they are going to have a heart attack, and so on. And all this kind of data they introduce in the computer with an algorithm in the classical statistics. Finally, I have a results, and I know if the difference of death between two populations and so on. But in machine learning, I introduce all the data, and this data introduces in the computer create with a learning process a program, an algorithm that is able to recognize in the next patient I introduce if this patient is going to die or not, is going to have a heart attack or not. What does it mean? Does it mean that all that I introduce in the program, I am able of put a label. If this patient have a label that says if he's going to die or not, the program starts to recognize these kind of patterns of death or not in order to be able to create an algorithm to afterwards to create the possibility of individualize the evolution of this patient. This is we call the supervised learning processes. But also I can introduce a huge amount of data with any kind of labeling, and the program is able to create different kind of patterns. This is unsupervised machine learning. So in this context, if I am able to recognize this, the next step should be to know that there is different kind of machine learning. And this is important for the clinician, because sometimes when the clinician says, well, it's not my role to know nothing about artificial intelligence, I hire the services for engineering, and I have a fantastic engineers in supervised machine learning, or a fantastic expert, better. I have a fantastic expert in support vector machine. Support vector machine is a kind of machine learning that's fantastic, and it's an expert. Anything is made by support vector machine. And what about all the different kind of machine learning processes? If the clinician doesn't know this, probably he's going to lose, or she's going to lose a lot of possibilities of the machine learning processes. For this reason, it's very important to know the scenario, how it works, all this. Because finally, the confusion matrix, the results to be analyzed by any kind of system, classical statistics, artificial intelligence are the same. The confusion matrix are the same. Usually here is very easy to understand for us this kind of imaging. I have to know the predictive value of our result, the sensitivity, specificity, the area on the curve, all is the same. And the third source depends of the clinical perspective. So finally, in this context, you have to recognize that I'm going to have a scenario where the decision of the aim depends on the clinician, the interpretation of the results depends on the clinician, and how you're going to get the results with this algorithm depends on the work of the engineer. But if there is not an overlap between these two specialties, the knowledge is impossible to arrive to a very good end. Well, in order to put some examples of this, we're going to the next step, that is modeling algorithm optimization and how to extract the knowledge to create predictive models. Well, now, because all these kind of concepts sure in a more fantastic way should be explained for a technician in this kind of models, but I'm going to give just a glance to the main issues to recognize in predictive models that are the possibility of machine learning. First, we can describe our sample. Second, we can add diagnosis analytics. You can look for patterns for diagnosis. And probably one of the more important one are predictive analytics to predict what's going to happen with this patient, and even to predict what is going to happen after an intervention in one patient, after a surgery, after endovascular procedure, after to give a patient, what is happening afterwards. And this is probably the main future of artificial intelligence. Because finally, and this is one of the more important slides also in this presentation, you see in the column of the left, in this square, I have different kind of dots, red and blues, and I would like to recognize, I would like to know how to differentiate in two groups this. Usually when statistics, I able to pass a line in the best way in the middle, with some risk of gain or lose positive predictive value or negative predictive value, associated specificity. But really, I would like to have a line that goes in such a way that I can differentiate with a high precision, accuracy, these kind of groups. Well, this is artificial intelligence. This is a different kind of models, artificial intelligence, nearest neighborhood, supervision machine, decision tree, random forest, neural networks, and all these kind of processes give us the opportunity to get an important results in the confusion matrix with the possibility of good or good result. But if the engineer works alone in this process, for instance, they took the decision of use this kind of model, probably is going to get a fantastic specificity, but always sensitivity. But if I want to create a screening test, I'm going to need a high sensitivity. If there is no connection between our two fields, then the results are going to be are going not to be useful. Understand me? Or for instance, one of the more powerful methods are neural networks that depends on a black box where the interrelationships between all the variables create a decision process that have a huge accuracy and precision, but probably I don't know what's the more relative variable. However, another processes like random forest give us the opportunity to prioritize the importance of the weight of the variables. So now it's easier to understand probably the relationship that we need to create between engineers and faculty. Well, because finally we are going to create, with this database, with that data set, we're going to create the infrastructure to collect the data. We have to prepare the data. And finally, with these algorithms, we are going to train all this data to create an algorithm that finally is going to go to the real life in order to give us the opportunity to individualize the decision process. But any kind of algorithm should be validated, evaluated in order to see if I'm going to transfer to clinical practice. So this is the end of the process. Well, the Industry 4.0 that has arrived very quickly from the industry field have arrived to health. And it's amazing in the last few years, we are just here, the increasing of the value of these projects. This is money. This is money. And here you see the perspective in a couple of years. And here you can see how the half of the market is in Asia Pacific area, mainly in China. These are the main fields that are imaging, there are discovery, already diagnosis, therapy, and so on. And this slide that is crucial. You should be aware with this kind of imaging. This slide gives us the opportunity to think that, and this is the FDA approval processes. This slide gives the opportunity to see that all these different kind of algorithms are introduced in clinical practice. All this specialty and all these close to 40 algorithms are in clinical practice in the United States. So if we create some kind of algorithm, we're going to produce an algorithm, we're to put in the market this algorithm. With the money we get is going to be refused in our research processes, but finally the results are going to go to the patient in order that the doctor, with the signature, take the decision of do something with the results of the algorithm. This is the final photo of all this process. Well, this is a couple of days ago. This is the research with only 2 words, artificial intelligence in PubMed. Here you can see how it's increasing. This is the last year, really stopped by the COVID probably, and how it's increasing now. This is amazing. We are just now in the middle of the starting of the storm. Well, now a few words. In this context, we're going to give you a few words about the application in the techniques, or this kind of, once I put you in the context of how it works, artificial intelligence in the field of health, I would like to introduce you to the field of nephrology in order to give you some perspective how it works in the state of the art, and after give us our experience. I want to give some points of view of what is the state of the art just now in nephrology, and I would like to demonstrate you how we, with our teams, could work in our hospitals and give some surprising results. Well, the state of the art. Few slides of the general field, not in nephrology, but in fields very close to nephrology. For instance, predictive models in mortality, here in the left. These are the classical models with classical statistic, for instance, Framingham, that all of you know very well. Artificial intelligence, machine learning. Here, with the prediction of mortality with imagings of electrocardiogram, infarction. Here, the columns in the left, traditional processes. In the right, machine learning. The right, imaging, diabetic retinopathy. Here, in the bottom, all related with the previous models. Here, up, already machine learning. Accuracy, 89, 96%. This is amazing. Let's go to nephrology. This is all these articles are from the last couple of years, last year or even this year. Promises of big data artificial intelligence nephrology transplantation. This is all the databases, most of them open, really to connect or to make trial, to use your hands in order to connect with this data, and that are able to be used with machine learning. This is all just a glance, some reviews, and you can see that the half of the United States and the other half from China. IgA nephropathy. This article is published in the Kidney International from the last year. Do you see the authors? You know who is Carmine Socali? Do you know Rosanna Coppo? Or, for instance, the people of the group of Prague, Tessa, they are working with this. This is a sample of 1,000 people, where 15% of the patients are used for validate the model. They use the classical statistics, the cost regression model and so on in order to select the best variables. But after the joining one of the best variables for the correlation models with the classical variables like age and sex, and with the variables that could influence in the model. And they realize that they can get in 5 years, here up, or 10 years, an area on the curve or 0.8 or 0.89. Nephropathology. These are 2 journals you know very well, or the first quartile, the NDT and the Clinical JSON. Nephropathology, amazing work, where even if we use the capacity of analysis of the imaging, like here, and this is joined to all the possibilities of the rest of the data, not only demographics and diagnostics and so on, but also even omics, genetics, and so on, the capacity of introduce the neural networks in order to classify the patients of different diagnoses opens the field to a capacity of interpretation that is huge. Or, for instance, this article for pathology, where once the system have been training and we have classified the different kind of resulting biopsy from sclerosis all related with proliferation in specific with cells, mesangium, and so on, we go to different steps, machine learning processes. We compare the results of the different diagnoses, all the different analysis of the biopsy, what says the area on the curve, and the opinion of the nephrologist. And here you can see, here in global sclerosis, probably it's not very difficult, where is the nephrologist, or in another analysis, where is the nephrologist and where is the area on the core. Well, hypertension. In hypertension, there is a lot of models related with prediction, with management, and so on, and with success. But that is very amazing is that if you see, and you will remember very well, all the clinical trials related with hypertension, the last 20 years, already with different kinds of drugs, the channels, the calcium channel blockers, the H inhibitors, diuretics, and so on. This is all the randomized clinical trials. In these last years, how many clinical trials there are? Nothing. And this is previous to the pandemic, because all goes to genetics. This is a graphic that shows what's about the Moore's law. The Moore's law says that every couple of years you can double the capacity of the computers. Even in 2003, for analyze the genome, costs 2.7 billion or 2.7 billion American billion dollars, and to do the same in 2016, 700 euros. This is the reason why now all the analysis on hypertension goes to genetics. Well, another point is acute kidney injury risk, acute kidney injury risk. A fantastic review made with Joana Gameiro. Joana Gameiro is a fantastic doctor from Portugal. He was rotating with us. And Joana made an analysis of, I'm going to put you here 3 tables of acute kidney injury, taking into account the models with, most of them with a CAT-DIGO definition, and with an area of the under the curve and sensitivity specificity with really impressive values, 0.7, 0.8, or sensitivity or specificity that goes to 90, 94%, and so on. Chronic kidney disease progression. At this point, I would like to introduce you not only the capacity of the machine learning for analyze all this data, but also that we also should consider a different kind of machine learning processes to analyze the data, not only one. For this reason, it's very important the collaboration between clinicians and engineers. These are the different kind of machine learning processes. And you can see here that probably some of them are very similar, but some of them are very not quite good, or another kind of analysis, some of them can be better. For this reason, we also know the benefit of this kind of analysis, but not only the raw curve, but also the sensitivity, specificity, and so on, that depends on the aim of the study. Because here, in these results that depends on the confusion matrix table is where the clinician is going to speak to the engineer to see, we are going to select this or this or this. In fact, finally, in the interface of the computer system, I can introduce all the data, but finally I have to choose, because the engineer says, well, up to you. Choose the better one for your patients, and you can use one of these models in order to have your results. And the idea in future, not only to introduce your data. The idea is that the system take the data of the computer and after give you directly the result. Well, even although machine learning is created for big data, with this methodology, we can use it even for rare diseases. And this is crucial, because rare diseases sometimes is very difficult to be analyzed, because they're very strange. They have very different relationship between the variables. That's the reason, because the machine learning, as loose for hidden relationship between the variables, have the opportunity to give you results in rare diseases. Well, now I'll give you just some slides in order to explain you from our perspective, what are some examples of how machine learning, how can be used in your environment. I'm going to put you 4 examples. One, how can you train your people to use the data? And this is a model for mortality in acute kidney injury diseases, prediction mortality with open database. I'm going to speak you about how to create a prediction model in chronic kidney disease. And after, what happens if we compare classical statistics with machine learning? And after, how even we can create a decision, some kind of algorithm in order to take decisions immediately in the better of the patient. First, I could put you the same slides of our student. This is a student that came from the University of Pompeu Fabra that works with our team. Our team that is composed by engineers engineers of the Autonomous University of Barcelona and of our research group in the Hospital Partolí, an environment of our mixed unit between engineers and and our department, we have some kind of students, and this is a student that came from University of Pompeu Fabra in the degree of biomedical engineering. We say, well, you have to be trained in this. Then we use an open database from the huge hospital of Boston, the Israel Diaconate Hospital of Boston, and we take a amount of data, really raw data, with a lot of missing, a lot of problems. We probably difficult to group all this data, and we train it to select the data, to prepare the data, to clean the data, to make the interpolations, to work to organize all the data to be interpreted by the machine learning processes in order to unify the criteria to be interpreted and so on. And in a context where, as the mortality in this kind of space is huge, to interpret it, we can create an algorithm. This is the previous results in the literature, okay, with also with artificial intelligence. These are under the curve, accuracy, and I'm not going to speak really of the results, but the methodology. Well, our aim was to look for mortality, and then in order to train the people, we went for the different phases. What happens in literature, how to extract the data, to use the classical statistics, and after to use different kind of algorithms in order to know what are perhaps the more relative variables and to create the best predictive model. Well, very important point of view. I have to select the data. Then I can use all the data or use the data related with the literature. For instance, the SAPS2 are a system that creates, in a more specific and sensitive way, the prediction of mortality in acute kidney injury patients in intensive care units in literature. I can use only this data, or I can use the data of an expert. I take a nephrology. Please tell me what are the main data for you, or I can select the data depending of. I don't want any missing, only without missings, or with all the patients. And although I have missings, I create interpolations in order to cover these missings in order to have more data. Well, I can make a lot of combinations. Finally, the confusion matrix are going to be the same, as you know. And after, we can use different kind of machine learning processes. And finally, when I have the results, the sensitivity, specificity, predictive values, and the curve, and so on, I can have different combinations. And these combinations are including the classical variables of the literature, or only that, or adding more variables. And here you see the different number of patients included depending on selection process, from 4,000 to 15,000. And here you can see the different results in this table. And what does it mean? That finally, and the conclusion is that, curiously, the better system is when I spend a lot of time taking as much as variables as possible, and most patients, and even with the missing, but covering the space of the missing. What does it mean this? That probably the power is more than the data, than the decision-taking process of the selection of the clinical data and the clinician. This is wonderful. Other point is a work that we did really with our electronic health records in chronic kidney disease. Well, for nephrologists, as Dr. Cruzado told you before, chronic kidney disease is huge in the world. It's increasing in the Western countries in a huge manner. And the problem is that most of the patients are related with diabetes, hypertension, and so on. Then, for us, it's very easy to understand, well, we have to take care of the hypertension, diabetes, and so on. But the problem is we cannot identify the patient on risk of dying or not, because sometimes we invest a lot of time and money and resources in a patient that is going to die, and perhaps is not useful, and perhaps we lose the opportunity to invest in a patient that is going to die, but we don't know that this patient is going to die. And this is very important. In fact, this is a publication of the European Society of Nephrology, where we can see in the dotted line the mortality evolution of the normal population, and here in green, the mortality of dialysis patients, and in pink, the mortality of the transplant patients. And this huge gap is where we have to work in order to recognize the patient's risk of death. There is no predictive models in the general literature for this kind of patients. There is no models in the kidney patients that are applied in clinical practice. And this is the reason that we work in this. In our population for our hospital of half a million inhabitants, we take all the patients of the last 30 years in dialysis, and we do the patient that we have for the huge data, all the data in the electronic health records. We select 260 patients, and we take all the diagnoses, and we make different groups of diagnoses until we select the diagnosis, all the lab tests, all the data related with dialysis. And we order this data in order to obtain the possibility to identify the patient at risk of death, but when is going to die this patient. we use it, a random forest, in order to recognize what are perhaps the variables that are more contributed to the system. On the other hand, the neural networks, you need to identify the patient at risk of the model. If this is the classical neural networks, we have different cells and relations between them. This relationship of the cells depend on the incomes of the information of different variables and the outcomes for finally identify the patient at risk. So, and this is the work of the mathematician. And the important point here is that probably we are going to discover very important relationships between the variables, some of them hidden that we are not able to recognize, but are able to identify when the patient is going to die. We have to spend a lot of time preparing the data, not only to select the data in order to be analyzed, but also to classify the data in order to be according to different slots of times to be interpreted by the algorithm. And after this, the rest of the data and so on. And this is the survival curve, and this is the training process and so on. And this is, for instance, this is very important, the number of features are the variables, and what are the variables that more contributed in the prediction model. And finally, this is the main slide. Here, we make different combinations of the data, different combinations depending on different variables, depending the expert, labs, and so on. And finally, all variables included, but very well working the pre-processing processes were the more effective. Even here is an example using only analytics, only hemodialysis, or all the variables. All the variables are powerful. And this is that we go really real world data in our computer. So the probability secret is to use the usual data, but very well worked. And this is the prediction in different steps, to 1 month, 2 months, 3 months. The mortality, that area in the curve goes from 0.75 to 0.87, better or equal, at least equal to the literature, and even more better than some articles. Well, this is a fantastic review about, this is curious, this is a work presented in last meeting of the JEMAD, the National Society of Nephrology. This is presented by Nuria Molis, one of our fantastic biomedical engineers for our team, and this is working by a medical engineer, in order to emphasize how can work an multidisciplinary team, where we review the same data of article that we published 2 years ago in order to recognize what are the predictive variables related with the maturation process or the long-term survival of an arteriovenous fistula for dialysis. Here you can see in the short term, the more related variables, and the long term, the more related variables were the age and the Doppler examination of the diameter of the vein. This is logical. And the long term, the velocity of the blood, the peak systolic velocity. Well, the decision was with the same variables, analyze if the results were the same. It means the age and the characteristic of the vessel by Doppler ultrasound. And we analyzed this with random forest in order to know the relationship of the variables with the outcome. And that means recognize what the variables more related with the outcome. Here we go with different classes of processes. We discovered that the order of all these variables was like this: age, phosphorus, PTH, ferritina, calcium, hemoglobin, and afterwards the Doppler ultrasound. And I work in Doppler ultrasound. What would you think of my feeling when I see these results? In fact, we saw that the more related variables were the mineral metabolism, the second inflammation, and afterwards the Doppler ultrasound. Well, and finally, for finish, this is a couple of slides. What about imaging? In arteriovenous fistula, for measure the flow of the arteriovenous fistula, I need to use Doppler ultrasound. And it means to spend some minutes in order to put the Doppler ultrasound, train, and so on, in order to see the flow. But with imaging, I can recognize the flow. Probably it would be a fantastic success, isn't it? We make 3 groups of patients, lower than 750 milliliters, from 700 milliliters to 1.5 liters, and higher than 1.5. And we use infrared thermal imaging in order to classify all this. And we discover that, and here you can see some examples with a patient without fistula to a high flow fistula, that only with imaging, just with a photo, with the algorithm, we can recognize with a huge specificity, positive predictive value, and look at the curve, fantastic results. Although we have to optimize this, because for instance, in the medium flow, the positive predictive value is not good like in the higher or lower flow. But you can see how this works. So in summary, after all these results, the conclusions that from the skin of a clinician could be that the main keys of the paradigm shift from evidence-based medicine to data-driven medicine lie both because of the possibility of personalized medicine, but mainly by the lower risk of bias. It is as important for the data engineer to join the multidisciplinary team as it is for the clinician to be able to understand him. If we don't have training, we are not going to understand our results given by an engineer. It's like statistics. He's going to join apple and pears. So the incorporation of the clinician to the IA involves knowing each and every one of the new components of the new ecosystem. That is the resource management, minimal technical knowledge, and minimal technical knowledge that as much as you can should be better for the team, and the ability to manage a project. This is crucial. If we want to get money, we have to create a project. And finally, the responsibility for the success of an IA-based product depends on the evaluation of the test, its applicability, and this ultimately lies in the arena of the healthcare professional. So we have no choice but to play the game. Thank you very much indeed. I would like to that you maintain your rating this put please the last slide that pon por favor la última diapositiva que habías que estaba. I would like to that you maintain your rating. You take home these couple of messages that I love. One for Niels Bohr, one pioneer in the quantum mechanics. Pioneer in quantum mechanics, that says, is not by improving the candle what we have invented electricity. I worked a lot of years in evidence-based medicine, and I recognize you have an important limitation. Probably this is a new world. And probably we have to think, that is the point of Darwin, that we have to fight against the resistance of the system, because probably when we have to invest or get money for our system, the resistance of the managers of the hospital, the managers of the administrations, and sometimes one of the bottlenecks. And we are the responsibles of this change in the roadmap on this scenario, artificial intelligence. We shouldn't be stronger with our usual tools. We should adapt to the changes of Industry 4.0. Well, that's all then.
Thank you, Josep, by this interesting and nice presentation. Now? Okay. Thank you for your nice and interesting presentation. We have several minutes for some questions. I don't know if somebody in the net are questioning anything. No? So we start. Yes, enough questions. Yeah. I'm very interesting about the data. All the work to collect, to clean, to mining, most of the results depends on the quality of your data. And a lot of literature in different centers, they are publishing their results with data that you don't know what is the quality. So what do you think about the share of data between centers to create one big algorithms to predict the same disease that are worrying us?
Well, this is the second bottleneck. The first bottleneck is training. The second bottleneck is how to select the data. If you have no training, you know how to select the data. The data depends on the work of the clinician, the expertise. This is crucial. You have no opportunity, you have a problem. And second, how to select the data from the clinical point of view or technological point of view. That's all theoretically. But from a practical point of view, you have to work on this. Because if there is no people that work with this data from this point of view, probably you're going to have problems. How can you recognize that you have a problem with this data? With the validation process. This is to understand. Because sometimes probably the people that work with training, with collaboration, with interdisciplinarity and so on, with methodological processes as well as they can, they're going to get results. And when they validate the results, they confirm this. But sometimes you are working in two ways. One, without spending time preparing the data. On the other hand, you can spend time preparing the data, but if finally you don't validate your results, you don't know what's the better, because probably the people that think that have not validated the data, they work quite good or not, and the other people that work it a lot, perhaps they are fantastic, but they not. For this reason, the more important point, and there is no validation in the literature usually yet today, this is the secret. But in any case, if you think that you are preparing, you're working very well preparing the data, but finally you have your feedback, you're wasting time. The point probably is this. And the other point that we should be aware is that we have to create a roadmap in a very systematic way. And this is crucial because sometimes we are intuitive. And like in evidence-based medicine, that the people confuse this with experience-based medicine, with engineering is the same. Then you have to make a checklist, a roadmap of how you work from the clinical and technical point of view. And this way, if you don't work in this way, this has no sense. It's like when you prepare a work and you give data to the statistician without speaking about your project. This is a question of common sense.
I agree with this roadmap, but who has to design this roadmap? Because it's very interesting, this slide that you present, that with the same data, different experts take out different conclusions in these guidelines from, for example, the Spanish and European Society against American. So what do you think about the role of the expert, how to choose the expert? It's a collection of experts and maybe it's the summary of what they think, because it's like to see the elephant. Somebody is taking care of some place and maybe we are losing the whole problem.
This is I love this slide of the the tail of the Indian elephant, the perspective of the animal. Well, the promising results of the artificial intelligence are based in that are lower depending of bias of the human thinking process, not like in guidelines. In guidelines, the experts are really pause. I think that, and we are used to that. But in artificial intelligence, if you are an expert in your field, and you are an expert in your field, clinical engineering, and you say, we should do this from a technical and clinical point of view, as you don't know the results, because in the interpretation of evidence-based medicine, you have the results of the methodologies, and then you say, I choose this. But when you work in artificial intelligence, you work from a technical point of view, and finally you are going to have a results. Sensitivity, specificity, predictive value, accuracy, F1, and so on. And then, depending on your pathology, you are going to choose one system or other one. This is a completely different concept. So probably the future of artificial intelligence that works very well in industry, if you work in the same way with data in medicine, the results should be the same. Sure, this is a dream, but probably we have the antecedent of this in the industry. And we have a very important responsibility because finally, we, the clinicians, have the knowledge of what we want and how to interpret the results. And finally, we are going to make the signature of the decision to the patient, take this drug or other one. And finally, when you are going to into computer, the idea is that the real world data of the computer be taken by the decision process software. And finally, in the right corner of your computer, the patient is in red, in yellow, or in green. And the patient is fantastic, but it's in red. You have to give a drug or not. Well, then if you are not related with the creation of this software and the person of engineers, or the clinicians that use this software to prepare it are not involved with training, what are you going to get? In any case, finally, the validation process is who is going to give you a responsibility to say, I'm going to use it or not.
Okay. I would like to keep going on the topic of data themselves, and probably shooting my own foot because I always have this feeling that even when we come here to talk about artificial intelligence, but basically all the problems are about the data, not about the artificial intelligence itself. And again, going back to what I said before, we've been doing artificial intelligence as applied to medical data. I don't know, it feels to me like forever. But still, we seem to be kind of like mice going around the same circles. And my feeling is that the problem is the data is not
I mean, the center of it all is the data, not the artificial intelligence in this case, or the machine learning, or whichever techniques or approaches you follow. And I mean, this is not just a question for him. It's actually for all the medical experts in the table. It's okay, in the end, if, for instance, hospitals are generating data, are beginning to now take digital data more or less seriously, but in the end, who is in charge of the data? Okay, who is going to be in charge of the data at the hospital level? And if we want to go to studies which are multi-center, not to mention international, who is ultimately responsible for centralizing the management of data? Because in the end, I mean, there is also a problem that I see here is that artificial intelligence has its own, let's say, requirements about how data should be. And with artificial intelligence, we are beginning to see, you know, a light on how to deal with very heterogeneous data unstructured from electronic health records, including text, signals, images, whatever. But in the end, you need someone in charge of the data. Where does this entity come from? Should be a political decision, should be a hospital decision, should be health system decision type of thing?
Yeah, this is okay, interesting question. Here, I think we have the answer, but we don't know how to approach the answer. The answer is easy. You will have only one system, problem solved. But the problem is that you depend on different companies and different hospitals. I remember a lot of talks in different meetings when this topic is on the table. And I remember some meeting with chief of departments on nephrology for the country that says that when they want to connect with other hospitals or other centers, it's impossible because the data transferring process is impossible depending on the companies. Or even in our hospitals, the problem was the same. I have the data of the hospital, I have the data of the lab, and to connect the store system of the lab, the hospital account, because the interest of the companies depend of the agreements with the health system. And sometimes if you want to open the door to collect the data, that can be from a dialysis machine, can be of lab, can be of imaging, depend on the agreement that you do with this. The data have some value. This value can be political, can be monetary, or can be related with some kind of work. Then, as you depend on these kind of environments, the interest of connect all this not depends on any center because any center wants this all data. And the clinicians are losing in this huge ocean with a little boat looking forward to reach Earth. And this is the problem. What should be the answer to this? Because really it's easy to do, because you have to work with privacy, you have to work with ethics, you have to work with a lot of issues, but finally the technical processes should be solved. And it's easy to solve. So there is a rule in informatics that says, and you can, as you do it, you can solve any problem you create. You can join all the different sources of data that you want. The problem probably is this political decision process. In fact, here, for instance, in Spain, we have the register of the kidney diseases that we give to Europe are given by the different communities. We have not a joint register in Spain. It's crazy. Why not? Why not? I make this question every day when I wake up. Why don't have we a register? Imagine in Europe. For instance, we want to create now, and Europe, I involved in the Vascular Society in Europe, as you know, and we want to create a pan-European register in vascular access in dialysis. And the work is to be terrific. But when you ask to the EDTA, or you look for the EDTA data, you see that the register are aggregated, disaggregated, the data depends on the country. Then if you want to create a parallel registry, then the first step you have to do is to involve the societies of all the different countries in Europe and from the 0 point to create the design of the register, thinking that everybody can use it for clinical assistance, for research, or for innovation. This is the 65.0. If the system are created, then you have to open the doors. But when you open the door, somebody always have some kind of concerns. And the concerns are security. That's not true. Because the laws in Europe say that you can have any kind of data on your hospital in out of Europe. The problem is that probably the hospitals have some kind of concern with the data of the hospital, but although we can understand this, that we don't understand the possibility of the join all the hospitals to join all the data. And this is a role of the manager of the hospital, the manager of the administration, and so on. Now in Europe are changing this. There is a roadmap in Europe about artificial intelligence that even in Spain, and probably the future is changing. I will hope that not in short term, but probably medium term.
Questions? Actually, I have quite a few questions. All right. Linking to data, still talking about data more than about artificial intelligence. And you have now mentioned this regulation of the European Union. I mean, we have the GDPR on one side, and we have this new regulation, which is tailor-made for artificial intelligence, but which, as I mentioned before, doesn't, at first sight, doesn't look that different to the approach followed by GDPR. Given that we still don't have this kind of centralized data policies, we don't have, or we are only beginning to have, like, you know, at the level of governance, bodies that manage and control everything, call it political, about data in a territory, etc. Hospitals, how they deal with their own data. How these GDPR and the new regulation of the AI do you think are gonna, and what are the challenges or the barriers that we might find? I mean, given that we are not even still at the level of unifying the data,
yes.
Now we have this extra kind of.
Yes, I love this question really because when you start any kind of work, the 2 points at the end of the road you have to be able to consider also, and you shouldn't forget, are ethics and regulation. These are the final bottlenecks. That you forget it, you are losing. Then these two are joining in the same point when any kind of project should be evaluated in the ethics research committee. And here you join the part of RGP, the relation with the protection of the data, RGP, and related with ethics. Then the new regulations, although they are more restricted, but on the other hand, are increase the capacity of mere research. But the interpretation of this are in the final step depending on the ethics committee. In fact, I had the opportunity in being on some of the meetings promoted by some public organization and with participation of responsible for the national health system, that even they say that are very difficult to interpret these laws. And finally, the interpretation, as is very difficult to consider in some aspects, and this meeting was a meeting of people of the Ethics Committee of Spain. And they told us, you as responsible of the Ethics Committee, you have to think probably that you have the last responsibility in the decision process of this. What does it mean? That you have the law, sure, you have a project to be evaluated, sure, but finally, or you have the consideration of this regulation, the system and the health system in Spain says you that the final interpretation depends on the table of ethics committee decision. This is the point where the last regulations in ethics committee in Spain, and I tell you this, like member of ethics committee in my hospital, should have the incorporation of engineering in this process. Why? Because, for instance, you have anonymization and pseudo-anonymization in the data. What about this? What's pseudo-anonymization? Because finally, when you anonymize all the data, always you have the possibility to recognize this patient. And even if you are studying a disease, you should be interested if there is some alarm to recognize what is the problem, to identify this patient and tell him that he has a problem. So for this context, probably it's better to make the pseudo-anonymization. Okay? Everybody knows the difference between anonymization and pseudo-anonymization, because depending on when you ask for data, the people that give you the data should not only anonymize, but also remove a lot of variables or even intervals of variables in order to make it difficult to recognize this patient. But sometimes until some limited because you want to pseudo-anonymize and not anonymize. First point. The other important point is that What about the informed consent of the patients? There's huge data of the patients. Then, depending on the disease that you are studying, perhaps you have to ask the consent, but are massive data. So who has the decision of give you the opportunity to make the study or not? The ethics committee. Third point, what about the security or related with the transfer of the data to some places that is not secure and so on? For instance, I have a grant, I ask for data, but how I want to travel the data anonymized from there to there, and where I'm going to store my data? Who is going to take care of the data? And because the people, you know that the people that anonymize the data should be the same that people that work on the data. Once they have the data, the people that work on the data shouldn't have the possibility to sue or record the anonymization of the data. And finally, with this data, I have to make some interpretation, and this interpretation can be of some kind of diseases where I should obtain informed consent. So finally, you have here the possibility of take decisions that depend on different fields, like clinician or engineers. So I think that the answer is not difficult. It's not easy, but probably now is with this kind of law is more open, probably to facilitate the research in this field if we use it in a proper way. But if we have no knowledge of how to use it, then we are going to have to lose the opportunity to use it in a proper way. I don't know if I answered you.
Yeah, quite. I mean, I think there is no kind of clean-cut answer anyway. I mean, it's a bit of a jungle. I'm asking because I mean, like someone who works basically on artificial intelligence, machine learning, it fills me with wonder. I mean, the things that doctors sometimes I see they have to do. You know, yesterday I was talking to before about this with Miguel. I was having a video call with an ophthalmology doctor in EDVABS. And he was telling me about how he has discovered, you know, in order to store his data, share it with us, etc., solid state memory. Oh, the solid state memory hard disks are the best. Now I can. Suddenly I thought, this guy, I mean, he's an ophthalmology, I mean, a medical doctor, a researcher in ophthalmology, and he's kind of glossing about solid state memory hard disks. You know, that's a completely change of, and that's because we were discussing about the problems he was having with an ethics committee about just doing a minor research collaboration with us at university. You know, he was, you know, spending hours thinking, should I put this data in a cloud, or should I buy Amazon Web Service to put them there so you can download it? Am I allowed? Why don't I use this solid state memory hard disk so you come here with your suitcases and you take it? It was kind of crazy. So I think it's largely a completely unresolved thing that is gonna haunt us for a long while. Anyhow.
No, but this is probably you have made an important observation, but this is our problem now. This is like when this is the same feeling that when you travel to some country that have no rules for driving, and you hire a car, there's no traffic lights, then you feel, then it's a jungle, and you use the common sense in order to save your life. And here are the more smart guys or not, and then finally you can have a bigger car. Well, the answer to this is that the future is that we need roads, traffic lights, you have a system, and this is now appearing in some countries like UK. UK, for instance, the first departments on artificial intelligence with people involved from engineering department and faculty are being created, and this is the future. And then you have any kind of that of ophthalmology. You go to your colleague, I have a problem in my eye, a problem in my ear, but I have a problem in my computer, and what can I do with my data? Because it's completely forbidden to have your data in your pocket. You have to put this data in a cloud. What cloud? Then you have some data. You go to the Department of Artificial Intelligence AI. I say, what is the safe cloud in this? And then you give you a card. Use this link. This is the password. Use it. This is the answer. Then you need these people in the hospitals. Now, what do we have? We have some colleagues, some friends in the Department of Systems of the hospital, information system of the hospital, or a colleague US engineer. Please tell me, we need regulations. And now this is changing. And this, I think that the administration now in the government in Spain and in particular in Catalonia, they are aware of this. And you know very well, Alfredo, that all of us, engineers and clinicians, have the same feeling that we need these regulations to be put in the table. And what's the problem really? Finally, the problem is that the data go faster than we, the regulation. As usual, what happened in the Far West? In the Far West, faster your finger, longer your life. And finally, we have the sheriff, the marshal, and so on. We need this change.
The last question. It's about the unit that you have been creating in Partaulí. It's in this line. It's to create a roadmap to help the direction of the hospital to put stress to take care of this intelligence, artificial intelligence applied to different diseases, to create software. What is your height?
This is a essential question for put an example of how we have to go to different steps in develop our structure. Well, we have created, we worked some years ago in artificial intelligence with a group of the School of Engineering at the University of Barcelona. I'm a nephrologist. In the Institute of Research and Innovation, the part of the I3CP is the like here the maps and so on is the infrastructure of research. And I have a group. I lead a group of clinical interventional computational nephrology, where we have a group for research. We worked with engineers some years ago, and then we realized that I have to go there, I have to come there, and we discovered that although we make a lot of processes in research, innovation, and even we created an educational program for researchers or for clinicians, that is a master that has been created last year with a huge success, and we are now starting the second edition in September. And we realized that the education, we work together fantastic in research, innovation. You have seen some of our projects. And we discovered that there is a legal figure, a legal system that is denominated mixed unit. The mixed unit that is very usual in some centers is when you want to unit different environments, completely different, like hospitals, university, under the same legal umbrella, in such a way that I can go to the department, to come to my department, some conditions, and I can apply to your grants, you can apply to my grants, and it facilitates. This doesn't give you money, but facilitates to get money and to create the environment to facilitate this. Came students, came researchers to create doctoral theses and all this. And then this works just now from in a context of research and innovation and so on, from university and the hospital. And this gives the opportunity to create the future probably that we should have in any department in our centers, where this is to understand the interdisciplinarity of different specialties from faculties, but also from engineers. The other point that you suggest is, what about the hospital? Well, this is not the aim of our unit. Our unit is for research, for investigation, for teaching, all this. For assistance, this should come from up. It's for the administration. And the administration should create departments in artificial intelligence or technology that should involve the people of the informatics system of the hospital, the clinicians, the legal department of the hospital, the ethics department of the hospital, the government of the hospital, and the people that is working on this. This is the point. And probably, who is going to create this? Probably the people that have more experience, and these people is going to come for the mixed units, usually. But the mixed units are really at the seal of this, because we have the knowledge. But really, all the related with mixed units of research depend of projects. Finally, they're going to go to the market and going to go to the hospital. But for the hospital, all the decision processes are related for the healthcare of the patient. And this is a completely different issue. This depends on the departments. So probably the future would be the same, but just now our project depends on this, of a department of the university for research, innovation, and so on.
Yeah, I'm actually quite interested in that last step or later step, which is, because this collaboration, academia, university, research centers, hospitals, in different guises. It's been around for a while, but the thing, what I struggle to understand, to be honest, is why is so difficult? Why is it so difficult to create a stable, call it mixed unit, call it multidisciplinary team, whatever, within the actual clinical setting? You know, people who are stabilized there as not just artificial intelligence experts, but data experts, the guys who are gonna help the medical experts to swim around the new problems of data science. You know, and I assume that there is a political issue there about, you know, governance and decision making. I mean, who can decide about the opportunity of creating those stable? Because in the end, there is an extra problem, which is even I mean, you can do research, you create an artificial intelligence model, whatever, but artificial intelligence models, as any other model, evolve over time. I mean, you need people updating those things. You need people, you know, creating the pipeline, the roadmap, whatever you call it, the pipeline of analytics that, you know, guarantee that as new data come, they become also part of the new models. They feed and update doctors. You need a stable thing for that.
For this, what do we need? This is a classical question. We need three things: experts, time, and money. Then the experts in academia, probably you have to look for them because sometimes you find experts, but they don't have interest in the topic. So you should have always in academia experts for this. Dedicated for this. The expert dedicated time and pay regular job, money. In clinics, it's even worse because only that Mikel or just I or some people in the audience work, we work on this in our free time, like volunteers, like a hobby. Oh, fantastic, Jose, you like this. Oh, fantastic, fantastic. Then this is have no sense. And you depends on your free time. And I'm very lucky because in these last couple of years, I got some free time because my hospital invested in me, giving me a little free time. This is wonderful because we have some grants, but it's finished. And we are some 2 or 3 privileged people in my hospital in this sense. You know how people work in some hospitals in Europe, United States? The people have 25% of the free time, even the half percent of the assistant time for research or innovation. And it's included in the salary. In this way, these people is substituting, is changing from investigation to innovation because they have the free time. And with the free time, they can create opportunities to apply for grants and get the money. Then I, in my free time, in my domestic area, I work on this like a hobby. You know, I have a lot of hobbies. What is this? Oh, this is crazy. Then who is responsible of this? The manager of the hospital, the manager of the administration. Then usually in the real world, the people that take decisions, they expect or they wait for see a critical mass of something to take a decision. But do we have to expect critical mass to take a decision in artificial intelligence? No. Now there's a department, an AI in the government in Spain dedicated for this, and they're working a lot. Yeah. But this have to arrive all the communities, arrive all the centers, all the hospitals, so on. And other question is, do the hospitals center wait that the wave arrives to them or not? Then it's like the classical tale, among all the people killed her, and they died alone.
Of her own, yeah. It's true because you know, when I started doing applications of artificial intelligence, it was in the UK while I was starting to do my research, and we were directly in contact. It was my first contact with people working with data, let's say, in hospitals, and they were statisticians, right? I mean, I'm talking about almost, well, a long time ago. In the UK, because you mentioned the UK, I thought, yeah, it's true that they are pioneers in all this. And the NHS has devoted some resources to that over the years. And the point is, you know, when we started to, you know, as machine learning experts, we started to go to hospitals and talk about data. It was with the statisticians. Yes. And the statisticians were okay, let's put it well integrated in the medical. So that's my conundrum. I mean, why statisticians have been around doing data science for so long in a more or less established way, and it's taking it so long for artificial intelligence, machine learning experts. And obviously, statisticians hated us with a reason. I mean, we were going there saying, oh yeah, look, your data. Yeah, well, yeah. We are the masters of the data. We are the statisticians, you know? And there was this obvious collision of goals between them and us. But I mean, I've always had this perception that data were already catered for. I mean, there was already someone there, you know, doing data analysis and whatever. And in one of your papers, one of the papers you have mentioned in your presentation, there was a solution in which, you know, a comparison of methods and logistic regression was on top. And over these last couple of years, I have had, precisely with people in the UK, this kind of ongoing discussion, because they defend that most of the supposed advantages of something like deep learning, there is lots of smoke and mirrors in there. And they say, I mean, and literally, we have been discussing about papers, meta studies that have been published, demonstrating or giving evidence that logistic regression is as good as any machine learning technique you throw around for many problems, not universally, but for many problems. So this takes me again back to this. I have the persistent feeling of deja vu. You know, we are probably going through some of the problems that statisticians have gone through, but statisticians are not fashionable. Even if we did the effort to go for statistical machine learning and merge with the statisticians, but still, you know, these. So the problems seem to persist, and well.
But I totally agree with you. But this is I have to congratulate you for these fantastic questions, Alfredo, because I feel that you have the same feeling than I from the other perspective. It's the same. You have summarized some of the more important bottlenecks that we have in the management of data. And one of the main problems in this approach is the resistance of the system. It's like, for instance, who is the more affected fields in artificial intelligence medicine? Imagine the radiologists are in danger or not. Because if they use artificial intelligence, they will increase their capacity and do better things, and they will have free time to dedicate to more difficult disease management. Then the problem is the resistance. And the statisticians are like this. The statisticians are two kinds of statisticians. The people that understand this is the future, and they use the classical statisticians, because we shouldn't forget, and I repeat this in every one of my slides, that the confusion matrix is the same in artificial intelligence one. And the linear regression is using by machine learning also. And you complement with machine learning the linear regression. And all these approaches that are the same should be adapted by all the specialties. In medicine is the same. It's exactly the same. In fact, for instance, I work, like Miquel, in some field in nephrology that's interventional nephrology. Interventional nephrology is a part of nephrology that is joining to interventional radiology, to surgery, and so on. And so the specialties are worried. This is my field. The patient is responsibility of all us. Then the idea is the expertise of each one of us should be taken in order to increase the advantage to have better results. Then the people of machine learning should know statistics, the statisticians should know machine learning, and the clinicians should know all of them. It's like overlap because the unicorn doesn't exist. In fact, for instance, we have been, you have recognized that. We have preparing a huge project, and we working with engineers, but also with statisticians. And the idea is always to do the same analysis with classical statistics and with machine learning. And not take the best one, but take the best one with perhaps the joining of the other one to complement it and have the best algorithm. That not should be perhaps, shouldn't be perhaps machine learning. You have to understand this. I love a sentence of an interventional nephrologist, that's a friend of mine, that when we speak about the borders, the frontiers in medicine, she's from Serbia, says, borders? The borders are changing every day. Then, in techniques problems on medicines, this is really like a Pangea. How was the world 1 million years ago, and how it's going to be in 1 million years? We are going to be the same. So, for this reason, the last slide was this. My last slide was trying to summarize that although we work a lot in the better way that we do, if we don't recognize we have to change, we're going to have a huge problem. And this is a problem. And we have to try that the people that think this way have resistant change. And this is the statistician, this is the clinician, this is the managers of the hospital, this is the politicians, everybody. And we have to spend a lot of time, that sometimes we think that we lose time. No, we have to spend a lot of time to try this. Okay, that this is part of your hobby.
It's a nice hobby you have. I don't know if we have already the next speaker ready or not.
Alfonso, it's not yet, so we could.
Yeah, I can keep.
Small.
I can keep talking then.
Presentation.
Yeah, sure.
Okay. Change the.
Well, thank you so much, Joseph.
A pleasure.
Very interesting.
A pleasure, and congratulations, Michael and Fred, for this very fantastic.
And to be honest, I mean, I was so much looking forward to the discussion, even more than the presentation itself. So
Sure.
it's been very nice. Thank you.
Sure.
Okie dokie. So a couple of things, I mean, until we get the next speaker on board, there are a couple of things that I left aside before. I didn't go for it. I did tell you about EDI and what we do and who we are and our skills and stuff. I want to go a bit further, right? Not with EDI itself, but with the idea, which was the core idea from the very beginning, that only now we are beginning to realize that we, as let's call ourselves artificial intelligence, machine learning experts, we really need to network in a way that we can influence how things go with administration, with the medical experts themselves, the medical community, who are also organized in their own way. By the way, something I was willing to say before, I didn't, but I also think it's, it's an important piece of information. I mean, we are talking about artificial intelligence here, but the truth, and Giuseppe's presentation somehow represents that, is that most of the artificial intelligence that is carried out right now and that we call modern artificial intelligence is mostly machine learning. Okay, because I mean we use these terms sometimes a bit loosely, and right now most of the artificial intelligence that you're gonna see that is gonna affect us in one way or another, and especially in the medical sector, it's basically machine learning, which is just a subset of artificial intelligence. And in fact, although this could be even a bit controversial, deep learning, it's a subset of machine learning. Okay, it's just that it has taken in, it has become so relevant these days that it seems like artificial intelligence is deep learning, machine learning, it's something different to deep. Well, it's not. Machine learning is a subset of artificial intelligence. Deep learning is a subset of, or even a kind of prolongation of machine learning. And I'm saying this because also we use kind of indistinctly the terms data science and data mining and etc. They do not all mean the same. Computational intelligence, but we have to bear in mind that in this reincarnation of artificial intelligence, we are mostly talking about machine learning. Okay, and machine learning is a very wide paradigm by itself. Because I wish to say machine learning is something specific. It's deep learning, is artificial neural networks, but it actually goes a bit beyond that. And even that's controversial because not everyone agrees what's within and outside the borders of machine learning. Again, another type of shifting border. Anyway, going back to the to what I was trying to say, one of the outlets that we are beginning to kind of consolidate right now as we speak on artificial intelligence is this network called IA Biomed, in Spanish, Inteligencia Artificial en Biomedicina. And this is again a sort of virtual arrangement. We realized that there were so many universities, so many research groups within universities doing biomedical research that someone, quite wisely decided that it would be nice to ask for a grant to create a network, a formal network that can exchange information, that can exchange expertise, that can inspire each other if you want. So right now we are organizing the second workshop of Spanish artificial intelligence research groups in biomedicine, this IA Biomed network. And as you can see, I mean, it's led by people from also from Catalonia, David Riaño from Universidad Rovira i Virgili. But it's, I mean, there are people involved from all corners of the state. And by the way, this is just, we could almost call it a special interest group within the CAEPIA, which is the Spanish official organization of artificial intelligence. So we are under the umbrella also of artificial intelligence in Spain in general. But this is something in the making, I insist. I mean, all these networkings are happening as almost as we speak. If anybody is interested in the Twitter account of artificial intelligence in biomedicine in Spain, this is the Twitter account. Also, I'm going a bit local now. Another network just created, Chartec Salut, right? Which is the Catalan network of R plus D plus I in health tech, as they call it, health technologies. This was created with 47 research groups in Catalonia, belonging to 17 different institutions. And it's actually led by the UPC itself, by the Krebs Center at the UPC. You have a link here. It's a big effort to create networking at the Catalan level in this area of research. Information technologies, not just artificial intelligence, information technologies as applied to medicine. And you can see the number of institutions involved. It's quite impressive. I mean, we have UPC as coordinators, but we have UOC, UVic, UPF, Rovira i Virgili, University of Girona. I mean, almost all the main universities in Catalonia, UAB, and UB as well. But we also have the EuroCat Research Center. We have EDVAPS, we have EDVEL, we have several hospitals involved. So it's quite a comprehensive network of interests for research and development and innovation in technology. And the last one before, because I think our next speaker is already online, I wanted to mention CIDAI, which is the Catalan Innovation Center for Data Technologies and Artificial Intelligence, right? Again, something that is being created as we speak, is coordinated by EuroCat in this case, which is Catalan Research Foundation, but it's meant to somehow also help to centralize this kind of hub in between the Catalan administration and the artificial intelligence community. Right? We are right now writing a white paper on artificial intelligence as applied to health, because one of the main tracks in this center is precisely health and medicine. I mean, there is also smart cities, industry 4.0, etc., other areas, but health and medicine is one of the main ones. So, I mean, basically, just to summarize, because there is not much more to say about this. I mean, if anyone is interested, you can have a look at the CIDAI webpage, which again, it's being built right now. But the bottom line of what I'm trying to say is that for the first time in, at least in my memory, there are like solid, real efforts to create a community around data science in health and medicine, and with artificial intelligence at the core of the data science concept. And without further ado, I think we can move to the to Alfonso, who should be waiting somewhere.
Okay, thank you, Alfredo. I think Alfonso Valencia is connected. Alfonso, how are you? Are you? Not sure if can you hear us, Alfonso?
Hello, good morning.
Okay, how are you?
Like everyone, busy and running up and down. I just finished my other meeting. I'm sorry I couldn't be here before.
No, you arrive on time. We are waiting.
I just left one of the commission people. I shortened his talk to 3 minutes just to be on time. So.
Okay. For sure, they agree that you have to be here and let the conclusions for the meeting.
I didn't let them any options.
Okay. Okay. When you decide, you could start with the next presentation, is about new in hardware innovation and high performance computing by Alfonso. Okay.
So, thank you. Well, first of all, thanks for the invitation. And I apologize because I'm not there in person, so I do this virtually. I couldn't make it to Barcelona on time for the meeting. So what I thought for today was to tell you about some of the things that we are doing at the Barcelona Supercomputing Center in this interface between the hardware and applications in this domain. I will try to keep this on time, say 40 minutes. There are a number of these topics that, as you will see, they are very much evolving. So that will be, I hope that will be a good opportunity for discussion. Let me share my presentation. So first of all, let me introduce you to the Barcelona Supercomputing Center. If you have not seen it before, it's one of the iconic features of Barcelona, one of the most powerful computers in Europe, in a chapel in the campus of the University Polytechnica of Barcelona, Catalunya, and the nicest computer in the world. The Barcelona Supercomputing Center, as you probably know, is not only the infrastructure hosting the Mare Nostrum computer, but it's also a research center. We are growing very fast, so we passed the 730 scientists and engineers working at BSC, so it's one of the largest institutes in Spain. There are 4 different departments: earth science, very much on the climate issues, engineering, computer science, and my department, that is the life science department, that is also growing very fast, and we are now more than 130 scientists working in different areas of biology and biomedicine. So now thinking in the discussion today, I thought we go back to one slide I have been using for a while about what are the difficulties of biology and biomedicine in terms of modeling. So what is represented here, a slide that was initially provided by Iwan Birne, director of the European Bioinformatics Institute, is how biology, represented here by molecular biology, is growing in data. So we are getting to a speed in production of data to the point that probably there are more data now in molecular biology than in climate or in astronomy. We talk about primary data. But our capacity to use this data to predict, to do predictions in different areas is obviously far less than the one of astronomy or climate science of high energy physics. And the reason, I think, is very obvious. The problems in medicine, in biology, are far more complex than the problems in astronomy and climate science or in high energy physics. For us, just to account for how many cell types we have in the human body, it is already a challenge, and just defining cell types is already a challenge. So we are still in a phase in which knowledge is not enough to develop models that are at the level of the ones in astronomy or climate that are used here as an example. I've been saying that still we don't have, even if we have a lot of data, probably given the complexity of all problems, we need far more data, maybe an order of magnitude more data of what is already available in high energy physics. And then the challenge for the future, let's say the next 5-10 years, is to produce enough data to be able to account for the complexity of biology, and at the same time, in parallel, develop models understood in a very general way to be able to use this data in a predictive way. So that's my initial thought about where are we with respect to other areas of science and engineering, and why. Obviously, again, a slide I have been using for a while is where we want to go. I think if I can phrase this in a single slide, will be this one. I've been using this idea of digital twins for the future medicine. The idea, the concept is very simple. In this case, the example is Anna. Anna has some condition, an accident or disease or something. Then she goes to a hospital where she has already another additional data collected. Probably she has already a lot of data collected from mobile devices and another continuous measurements. But then there may be other additional information that is gathered there, imaging or whatever. And all this together is sent to the digital Anna, the Anna that lives in a computer, the digital twin of Anna, in which obviously a number of conditions has already been tried, experiments in preparation for anything that could happen to Anna, plus the new data will update these experiments. Models will be generated and different solutions to the problem will be simulated and scored and sent back to the real Anna that is in consultation with the doctors and the team will take decisions about the course of action for Anna. Obviously, we know that this is far from what we can do right now. We know that there are digital twins are already in place in many areas of engineering, and they are a hot topic at the European level with many different projects in engineering. But we know that a digital twin of a real human being is beyond our knowledge. The question for me is this completely impossible for some kind of reason? Or is just a question of, like in the previous slide, accumulating enough knowledge and improving our models and moving in this direction progressively? And if we believe that this is going to be possible, is this going to be possible in 50 years, in 20 years, when and how we can approach this idea? Obviously, without thinking in the full model that will be useful in medicine, we can start thinking in models of part of the system. And as you know, we have become very good in doing models at the atomic level, simulating proteins and drugs, predicting drug binding, designing drugs. This has been going on for years, but now has really get to a stage that is becoming really realistic and is really part of the drug discovery process. In the other extreme, we have simulations of organs, simulating not only the physical movement, but also the electrostatic, electric aspect of the heart function, and this is becoming more and more realistic, and there are more and more chances of including in these simulations real conditions, specific personal conditions or disease conditions, and trying to understand how disease conditions or devices are influencing the physical model. In between these two atomistic and organ level, obviously there are many interesting aspects of biology that has to be taken into account, and these are the one I'm personally more interested, developing models of what is going on at the cellular level, all the intracellular signaling, all the metabolism, all the regulatory cascades, and what happened not only inside the cells, but in the interaction between cells, at the simulating cell-cell interactions. This could be the interaction for a given, it's not working, sorry. For example, the classical example will be a tumor with different cells evolving in different ways, different corresponding to different cell lines in the tumor, and trying to follow this evolution and try to predict the consequences of mutations or the consequences of the administration of drugs. Why I am interested in that, obviously, is because this is, I think, for the first time possible now. This was not, I would say, it was not realistic to try to do it a few years ago, but now technology has changed substantially, and we have, in the one hand, this type of single cell approaches, represented here on the left by the real single cell analysis, expression of RNA-seq in a given tumor. Each one of the dots correspond to a different individual cell for which we can have precise measurements of the state of the RNA expression that is representing the physiological state of the cells. We can separate different cell types and analyze this along the evolution of a given system. This is at the technical level, this is a revolution. At the scientific level, is for the first time, for us, for the first time, being able to know what happened at the individual level. At the modeling level, this is fundamental because now we can really think in developing individual models for each one of these cells, first of all, with pathways that will be adapted to different cell types, and then with information about the status of the pathways for different for each one of the cells. So we can do this in a more realistic level than never before by informing individual cells with actual experimental information. In the other hand, we have all these developments of organoids in which we are and obviously this is just at the beginning, but it's again another technical revolution, being able to replicate at a small scale cell types and organs, and this is progressing very quickly, so soon we will be able to reproduce in a more realistic way organs and then conditions in these organs, including drugs or mutations or any other condition. So again, from the point of view of modeling this setup like a target, we can start thinking in doing simulations that can be adapted or benchmarked against, for example, real tumors, but also against organoids in which many different conditions can be tried. So all this, all in all, that makes this type of simulations in which we are particularly interested timely and potentially realistic, having real experimental data at the single cell level and also experimental data at the level of intercellular interactions. Our aiming on all that is to be able to develop these models and to be able to use this model in a real biological or biomedical scenario. So that's just another way of representing this in a picture. This will be a very simplistic representation of a tumor, with the different colors are representing different cells that are in different stages. In this case, some of them are entering into apoptosis. Different cells can have different, or even of the same signaling pathway. The signal pathway will be acting in different ways depending on the different inputs, and the different input can be, for example, a drug or the oxygen conditions in different parts of the tumor. I'm not going to enter into describing specific results, but I'm just to say that we are in practice using this type of simulations with initial 1,000 of cells, mimicking or trying to model the reaction to different drugs and different conditions, and how these are influencing the evolution of this experimental system, model system, for example, in different doses of treatment. Again, I don't know why my simulation is not working. It's not working. Again, trying to reproduce known experiments using these simple systems. The current experiment I'm showing here are 2,500 cells. Our target for this year is to simulate 1,000 million cells in different conditions. That will be, this is what we are aiming to for this year. Obviously, there are many possible scenarios for the application of these type of technologies. COVID is in everybody's mind. This is a large international consortium developing maps of the interaction of the COVID-19 SARS-CoV-2 proteins with the human proteins, how this is interfering with different pathways, using this information of the detailed mapping of the interactions of the virus and human proteins to inform different cell types, and then doing simulations of epithelial cells in interactions with the virus and interaction with the different cells of the immune system, T cells, targeting different type of epithelial cells. So we can, not going to enter in the details of this specific simulation that is still very simplistic. In this case, we'll be simulating a catastrophic situation in which the immune system end up hitting all kind of cells, and at the end of the day, destroying the tissue. So again, I'm not saying that we can provide realistic simulations of these situations, but we are approaching to the construction of the systems to be able to do it. So we are doing this in the context of what is called a Center of Excellence for HPC. It's a new project. It's a Center of Excellence in High Performance Computing for Personalized Medicine. And our target as applications are this type of tumor evolution informed with single cell data, but also using non-single cell data, bulk genomic data that is probably closer to the medical applications, trying experiments with synergies, and also developing models for rare diseases. All this in this context is oriented to be able to collaborate with actors in different levels, from the health system to the pharma companies or the biotech companies, discussing with them how to include these models developed at the different levels in the research plan or in their development plan. Again, I'm not going to I think it's interesting, it's a topic for discussion later, what we can do in this area of simulations, how they can be integrated with other research projects, and to what extent or when this will be part of applications in biomedicine at the general level. In practice, what we are doing is we have selected a number of software that cover all these areas, from cell-level modeling to intercellular modeling, scaling them up, being able to run this in the high-performance computer in a way that we can aim for these simulations of millions of cells, each one of them with their individual personality. For the second part of the talk, I want to move to a different topic that is not simulations, is artificial intelligence and machine learning. And I thought in motivating this with something historical for Barcelona. This is 1995, and this is the first game between an IBM machine and a human player. The best player at the time in Spain plays in Mikel Ijescas, play again the computer that was sitting in the States. And you see here Miguel playing and then on the left you see the team on the other side. And this is 1995, so communications were pretty primitive, and the full game was difficult to organize. And you see in some of the pictures Mateo Valero, that was the organizer of this historical first game. The reactions, back to the previous one, the reactions to this game were interesting. This is the newspaper saying the machine will be the chess players. I found particularly interesting this that was in the same newspaper. Gil Carrasco, that was writing about that, he said that the machine, the Deep Blue, was very boring. The game was very boring, not imaginative, and was social-free, a call and without engine. And this requires playing chess will require some suffering and some geniality, and machines are never going to be big chess players. It's interesting that this is 1995, so it's not that far away. And there was at the time, it was still possible to think that it was impossible to beat the chess player. We know that this is by now completely gone. Any small machine will beat the best players, and this is from DeepMind. DeepMind is a company from Google dedicated to the exploration of machine learning. And this is a talk by the CEO, Demis Hassebais. And they have been playing all this game. Obviously, they solved the chess game long ago, and they were more famous by solving the Go game, beating the best player in the world playing Go. Go is by far a more complex game than chess. Because it's a game played by intuition, not only an strategies, not by calculation like chess. So I'm bringing this here because what they are developing is very interesting, but it's not because of the Go game. This what the Miss is explaining, that Go is a game played by intuition. And this was from a talk in the context of a CASP, that is the competition for predicting protein structure. So DeepMind has entered the prediction of protein structure because they thought that there's some similarity with the problem of Go, because you require not only computation, but you require strategies. And is a step beyond in a more making a more intelligent and open real-world application of artificial intelligence. So that's from the Guardian and the Vanguardian. The DeepMind, the artificial intelligence, cracked the 50-year-old problem of protein folding. Well, it's not exactly protein folding what they have solved. They have solved the problem of going from the protein sequence to the protein structure. They have not solved this completely. You can say they have solved this to the 95% or 99%. This, as you know, is one of the key problems in molecular biology, to which Sanofi has dedicated many years. Actually, I never thought that I was going to see this problem solved in my lifetime. These are results from CAS without entering a lot of details. CAS is a competition, has been running for many years. There is a competition every 2 years. So there has been progress along the year from the bottom to the up. This is a measurement of quality. The black line is the prediction of DeepMind. DeepMind has done this quantic jump from the previous one to the new one, and the numbers are around this 95%. So they almost solved the protein structure prediction problem. Thus, I'm sorry, they lost the format. This brings many questions. Some of them are on this particular area. If they have solved this problem, what is going to happen next? What are they going to do? What are the implications for medicine or for biology? This is one of the proteins from SARS-CoV-2. The prediction and the real structure is almost perfect. They can do this in a few hours. So in a sense, they can speed up the work in drug development or in development of antibodies with solutions that are almost perfect instead of waiting for the solution by electron microscopy or X-ray crystallography. The other questions, I will back to that, are questions about where is artificial intelligence going, what are the ethical implications, what are the resources dedicated to that, why a company can do that, and it's more difficult to do this on the academic side. And we'll be back to some of these questions. So this is a top-notch application. By now is the more advanced application of artificial intelligence in any field. Obviously, there are many other applications that we see every day in other areas of medicine. I took this one out of many ones. This is from January 2019. Nature Medicine, cardiology level arrhythmia detection, classified from electrocardiograms. And the results is that the electrocardiograms are easy to analyze and classify by a machine learning done by the experts. The crosses, the red crosses are the experts. The blue line is the machine learning. The machine learning is doing better because this is a very simple task. Is relatively easy when you have a few dozens of thousands of electrocardiograms. It's easier for the machine to learn the patterns once that you have, and do classifications. And humans tend to be distracted and to be less accurate and less stable than the machines. Nothing surprising on that for this type of task. I always bring in this type of scenarios this slide from Eric Topol. This is fine. These applications are going to be there, but they are not to replace the human. They are to complement the human in the task that they are better to do than the humans. And this is obviously not replacing the interaction of the medical doctor with the patients. It's just helping the medical doctors to do things that are systematic, like the classification of arrhythmias in the previous slide. I want to say something about the ethical consequences because once that you're talking about artificial intelligence, I think is almost is fundamental not to be aware of the limitations and to think about where are we going in some of these areas. I use here two examples that has been around for a while. One of them is classifying images of people cooking and asking a machine who is cooking. And whatever picture you show to the system, and this is already an experiment done, the system will answer she is cooking, a woman is cooking. Because women are more often in the pictures on the web cooking than men, and therefore the system is trained with biased data and is producing biased results. Same thing for the second example. The second example is on translation. A system is trained, there's a Google translator, to a sentence, she is the president, translated to in this case is Turkish, that doesn't have this distinction at this language level. Then you take the sentence again from Turkish to English, and what was she's the president will be translated to he is the president, because there are more sentences on that have been used to train the translator, in which is a he who is the president and not a she. So obviously mistakes these are simple examples in the training set that produce biased results. We are very interested in this type of problems. We have a full unit dedicated to analyzing bias and studying bias, in particular sex and gender biases as a scientific issue. The biological level bias in the medical domain, and these are, desirable bias. The physiology is different, and then it has to be studied differentially. And indesirable bias, like the ones I showed you for artificial intelligence. So there are obviously ways of preventing bias, but the first way of preventing bias is to be aware of the biases and really put the effort to counter the bias in the artificial intelligence systems. I use the moment to make some publicity. We are organizing this sex and gender bias in artificial intelligence and health, building the future for equality, as a series of conferences and workshops in the organizing Paloma Calla. So you look for this in Paloma Calla on the website. You will find a series of conferences and workshops, and you are more welcome if you are interested to join them. So I told you this development of artificial intelligence in one of the topics of medicine, predicting protein structure, that is very much related with drug development, but also how this is getting to many other areas. My last part is dedicated to natural language processing. Of all these are, again, this is a slide for DeepMind, where they were explaining the different type of approaches in deep learning, from convolutional network, recurrent network, graph networks, and to these attention modules. And it was very interesting because what everybody was doing, including themselves, 2 years ago in the prediction of protein structure, was the use of convolutional neural networks. And they changed their strategy in the last minute for this cash competition. So in a little bit more than a year, they changed their deep learning approach to an attention module, or the use of attention modules that were developed in the area of natural language processing. And then they catch everybody by surprise, because everybody was using something else. They were using something different, and the results are much better. And this, I think, is very interesting, because that means the plasticity of the technology. You can take something that was used in another field, in the language field, to apply this to protein structure prediction, but also means that in the future, in next years, this language of the different deep learning technologies is going to be dominating the applications in biology and biomedicine. And the new things we have to learn is the different applications, what they are, how they can be applied, what are the limitations, what are the possibilities. So in a sense, it's a new language to be added to the technology we use in computational biology. So the field of language, natural language processing, is the field that is progressing faster in artificial intelligence. The progress in the last 10 years is amazing, and we only have to see how the Google Translator is working, or the Alexas are working. All this is based in having models of the language, in being able to cast in an artificial intelligence system the structure of the language. The system we're using to understand or to do natural language processing were based on correlations. Now these are expanded to, if you wanted to see that way, to another higher level of correlation embedded in these deep neural networks. The models of the language are what are behind anything we do, essentially from the assistance of voice assistance to automatic summaries, to the answer and question and answering system, to the analysis of sentiments, to the diagnosis of images, to the conversational assistance, to the correct orthographic correction, to anything else. And all that is based on the use of massive data, being able to annotate part of this data, and this architecture of neural networks, building language models, and then using these language models or language of the spoken language, or models of first translation, and then developing applications on top of these language models. I'll give you one example. This is an European project dedicated to the reutilization of text in many different areas, because it's beyond biology. by providing systems that do anonymization and disidentification. Obviously, this is true in different areas, but it's fundamental in biology or in medicine. We need systems to be able to anonymize or pseudo-anonymize medical records to operate with them. So this is something that was very difficult. Now there are very useful systems that can be implemented in a relatively short time. We are very interested in this type of developments. This is part of a national plan for development of technology of the language of the Ministry of Economy, of the Secretary of State of Artificial Intelligence, and the Barcelona Supercomputing Center is the technical center developing this program. We are working at 3 different levels: at the level of Spanish, the models of Spanish, the level of Catalan, the level of models of the Catalan language, and the level of models on the biomedical domain. Part of the challenge, obviously, is to get enough data to train the models. We are talking here about 120,000 million tokens in the case of Spanish, 1,700 million tokens in the initial model has already been developed in a project of the Catalan government that is called ANIA for the Catalan language, and around 1,000 million tokens in the biomedical domain. So when I mean a corpus on the biomedical domain, this is the type of data we are using to train the systems, clinical cases, books, reports from the medical agencies, patents, the Wikipedia, the publication in PubMed, the publication in Cielo, all the publications we can get a hold, and this is what is used to train the models of the biomedical corpus. Obviously, needless to say that training this model has become very demanding of computing. The large model developed by Google has 1,000 millions of parameters, and this requires a computational capacity that is a challenge. For the Barcelona Supercomputing Center, with our potency of Mariner 4, we are on the limits to be able to train this type of models. Going to the application, this is a collaboration with just to give an idea of the difficulties of this area, as you probably are aware of. This is natural processing on clinical records or different type of clinical documents for COVID patients, developed in collaboration with the hospital clinic in Barcelona. I'm not going to enter into all the details, but we can do pretty well. This is the last table on the left corner, on the right side corner. We can do well on identifying diseases, procedures, and medications, and we are struggling to identify symptoms because it's a less well-defined category. Obviously, this requires a lot of detailed work. The medical records are a very specific type of document. It's embedded in a specific way of talking with a lot of negation, with a lot of abbreviations. So requires a lot of detailed work. Interesting in this project is that we were worried about the mixture of Spanish and Catalan, and turned out to be that the systems are very stable, and they can do equally well for Spanish or Catalan, or for the mixture of Spanish and Catalan that is very proper of the medical records. To our relief, because we thought that this was going to be far more problematic of what it is. So I want to finish with this some slides on the COVID-19 case. It's a collaboration with the Hospital 12 de Octubre in Madrid and the Hospital Clinic in Barcelona. We are hoping to add to these other hospitals. The first part of the work has been mapping, and this is for COVID, so mapping the variables that are used to describe the cases in different type of reports between the two different hospitals. And as you are very much aware, probably, certainly, one thing is to map the name of the variables. Something else is to be sure that these variables are containing information that is compatible between the two different systems or inside the two different systems. So they have done this work, mapping one to the other and being sure that the variables contain the same information. At the end, that is a substantial amount of detailed work. Many of the variables can be mapped directly from one to the other, but in many cases, they require a transformation. And that's, again, meaning developing methods, specific methods and software to be able to transform the variables to something that can be compatible with other hospitals. And now if we want to add a third hospital, we will need to repeat this experiment or this effort to be sure that we are talking about the same information. What we are using this information for, this information extracted directly coded already, or information extracted from the NLP effort. In this case, is a first example. This is between Hospital 12 de Octubre and a chain of private hospitals, Hospitales de Madrid, that they provide information about COVID cases, that is coded information, and we are using this to train neural networks. In this case, as the one I mentioned previously, recurrent neural networks with an attention layer to predict the course of the disease with different days of advance during the hospitalization, or predicting it backward in a way that we can have a retrospective assessment. And I would say with the data we have, the systems are working reasonably well in the prediction to the next 4 or 5 days of the course of the disease. Now we are trying to add a new data set from hospital clinic to improve the results, and in a sense also to validate the results. One interesting observation that even with all this effort to match the variables, given that the populations of the behind the data in the different hospitals are very different, we initially wanted to put all the data together to have a larger data set to train the systems. At the end of the day, this is not possible. It's better to keep the data separated because the populations are very different, and then to train the systems, different systems for each one of the hospitals, and then put the data together do one of these federated learning type of approaches, given the condition of the data. So I think we are still in a very early phase in which we are still learning a lot about how to train these systems and what is the relation of the system with the intrinsic bias in the data that is obviously undermining and determining the quality of the results. So my last ones are to put this in context, and the examples are from coronavirus. Obviously, these are individual efforts working with hospitals, trying to improve systems and to apply different technologies in the case of COVID. All this is part of can be put in a larger effort. This is the European Commission effort to build a platform for COVID-19 data and methods. This is organized by the Commission, by the European Molecular Biology Laboratory, and by Elixir, that is the European infrastructure in bioinformatics. The COVID platform is already there, is useful for tracking viral variants, but also human variants of COVID patients and all the related information. And in reality, this platform is a federated platform composed by the contribution of different countries. This is the Spanish COVID-19 data portal, that is a collaboration between the Barcelona Supercomputing Center and the Instituto de Salud Carlos III, in which we have different resources, as I said, genomic information from viruses and mutants, all the papers have been published, all the project that has been carried out in Spain in the context of the COVID-19, and the one I wanted to bring here in the context of the conversation about natural language processing in biomedicine is this one about the health variables. Also, what we are doing, apart of bringing the tools and methods, is mapping, following the standard, evolving standard of the Health World Organization, mapping all these variables that we are developing in collaboration with the Hospital 12 de Octubre and Hospital Clinic, and hopefully with others, mapping all these variables, making them accessible and providing the systems to make them discoverable in a way that we can connect this with the other portals, the European portals, and make possible the development of clinical trials, prospective or retrospective clinical projects, putting together cohorts by extracting information about the patients with this metadata associated to their variables. So that's part of finish with this, with a larger effort. This is part of the Spanish Bioinformatics Institute, that is the Spanish node of the European Infrastructure of Informatics. What we are doing together, a part of connecting the different bioinformatics lab in the country, is connecting with the and the research institutes in the Spanish hospitals that are part of this TrustBioNet network, in a way that we can collaborate with them in translating the collective efforts in the development of tools and methods in this area of biomedicine. And now we are putting all this together under what is the first effort, the first Spanish effort to build a personalized medicine project on the scientific side, so on the organized and financed by the Instituto de Salud Carlos III. The impact project that will be building this initial framework has really an effort in creating an Spanish cohort, an effort in putting together the chain of samples, sequencing, and reports. And our part on this project is coordinating the efforts to do the data analysis, and we will do this in collaboration with the TrustBioNet network and with the Spanish Bioinformatics Institute, and we are just at the beginning of this very challenging project, starting the Spanish, what will be the initial step in the Spanish personalized medicine initiative. Last, I want to just to say that all what I have said, from the simulations to the natural language processing, to the collaborations in putting together the medical information with the genomic information in the context of the initial impact project, will not be possible without high performance computing. The simulations, the natural language processing, are extremely demanding. Our Mare Nostrum computer, that is the one that is now running with the different components, is, as I already mentioned, struggling to be able to cope with the development of the language models, for example, or with these millions of cells, simulations of millions of cells in many different conditions. The good news is that we are getting a new computer, will be Mare Nostrum 5, that will be almost 20 times more powerful than Mare Nostrum 4. Is a significant change in the way high-performance computer is done in Europe, because for the first time, Mare Nostrum 5 will not be only a Spanish computer, will be a computer financed half and a half by the European Commission, and the other half by the Spanish government, the Catalan government, and the Portuguese government. So that is a 220 million investment that hopefully will put us in the condition to develop the models and the language models that we need to be competitive in the future. And with this, I finish with this overview of how technology is evolving, allowing us technology in the biological domain, technology in the medical domain, technology in the computational domain, in the artificial intelligence, natural language processing, evolving very fast to make us possible for us to make progress. And I showed you especially two areas on simulation and artificial intelligence that are moving really very fast these days. Thank you very much.
Thank you, Alfonso, for this inspiring communication. Now we have a turntable that it's open for questions. I don't know if somebody is asking, we don't have any question from the audience, so we could start. Alfredo?
Interesting talk, full of things. I'm specifically interested in this idea you draw up at the beginning about digital twins for patients. Because it rang me a bell. Well, I mean, we are working also with industry and this idea of the digital twins to simulate machines, high risk, high security risk machines. Obviously, it's catching on. I mean, it's really hot. But the point is that I saw something similar in intention. Like 15 years ago, it was a European project called, it was UK-led, called Biopattern. And they were trying to, well, basically simulate the patient digitally. But 15 years seems like, a really long time from the point of view of these things. So this digital twin idea, which you drop like, something for the future, it's been around for a while. But in the end, I always have the feeling that although the concept of digital twin, it's quite cool, to be honest, it's easy to sell, but in the end, it seems to me like mostly a matter of mixture of modeling and simulation. You model the patient on one side, and you use those models even to simulate data which are not there. And I wonder, and I would like to gather your opinion on this, whether this is a kind of, because the way you put it, it did sound like something like quite for the future. But don't you think that somehow that's where we are heading to gradually? I mean, maybe the digital twin, the way you put it, it's in the far future. But don't you think that something which is kind of halfway to this idea is not already on the making?
Yeah, no, absolutely. I'm not going to say anything different than what you say. I think it's a process. There is no black and white. We are building pieces of what will be a digital twin that could be comparable to the ones that are developed in industry for other for machines, for processes. The question is, if this as we are accumulating knowledge and models, I'm sure things will be going faster and faster with the time. If by integrating these models, we will be gaining additional bits of information and prediction capacity than by having the isolated models. That is a little bit what will be the added value of calling this a digital twin, apart of being a cool name. It's a cool name. So what I mean is that, yes, we are already developing models, and I showed you the simulations at different levels. And there are others that will be addressing specific problems in specific areas and will be useful, and there are models specific, interesting. Once that we can combine these models at different levels of granularity for different systems and having them really running for different conditions, I'm sure that we are going to learn a lot of things. We are going to have a lot of problems, but also we are going to learn more things about the system than about the pieces. And always that these things happen, the prospect of finding emerging properties is there, and then I'm sure that we will be getting to something that is more than the sum of the different simulations. But certainly what you say is true. It's a process, and it's not something we are starting right now. Having a cool name is a process of accumulating of things that has been already going on.
Well, Alfonso, congratulations for your excellent talk. It's really amazing, and not only for the capabilities of our capacity of machine learning, but also the infrastructure that we need sometimes for creating these huge simulation models. And in this context, I would like to make you a question, an open question to the table also. That is, I'm a clinician, I'm a nephrologist, and I'm just starting working in artificial intelligence in this field. And we feel that in hospitals we have just now the electronic health records. Most of them are structured data, and we are just starting working with unstructured data, mostly depending of imaging and free text, no, with NLP and with different kind of methodology in order to approach the test to try to stress some knowledge. In this context, related with simulation, that because in machine learning, we are to think in predictable diagnostics or prediction in some the evolution of some disease, and perhaps in prescriptive models. That means what's going to happen after intervention in the patient. But there is some step that is, there is no literature or few opinions that is what about the simulation in all related with morphology, dynamics, CFD, computational flight dynamics, are all related with the change in the morphology of the human being. That means more or less that was speaking a little Alfredo. Then the question is, where are we just now in all related with the simulation predictive models in all that it means 3D imaging, dynamics, and all related with the evolution of the diseases in aspects of 3D dimensions?
Yeah, no, well, this is, I mean, first of all, it's not my area of work, so I'm not an expert on that at all. Obviously, image analysis has been the area that has made faster progress in terms of image recognition. That's obvious, no? Because from the beginning, for the deep neural networks, images were easy to parse, easy to put in vectors, matrices, and it's like a very natural application for deep neural networks. This is and this is why there are many applications and very effective. The challenge from there to include dynamics into the system and to understand the relation between the dynamics of the system, the images, and the conditions is far more complex, and is back to the understanding of it's difficult to do that without, and this is why the interface between modeling and artificial intelligence is very important. It's very difficult to do progress in the dynamic simulation of systems based on images or anything else without knowing enough about the systems. And that's, I guess it's obvious, but it's easy to forget. Even if we have a collection and we try to replicate things and we can train systems, if we don't have a good understanding of the basic of the system and enough information for that, it's very difficult that this model will have a capacity to extrapolate conditions. And that's, I think, is where the simulations and the machine learning meet. Let me see if I can explain what I mean. That if we try to do only machine learning based on the information we have having models on the mechanistic of the systems, soon we find a limitation to the extrapolation of that we can do. If we understand better the system, understanding means being able to model them in a reasonable way, reasonable level of definition, then we will be able not only to extrapolate from the information we have, but also to add additional components. And this is a challenge to knowledge, because we know enough about the system to build the models, and it's also a technical challenge of how we are combining the simulation with the machine learning. So I don't know if this is answering your question, but this is one of the topics that is really important on this in this area and in general. This is why combining the two things is important. Sorry.
Yes, I was waiting an answer like this because probably one of the more specific questions that restrict the knowledge acquisition in this is really the expertise of the formulation of the question. And probably in this aspect, we need probably a specific mesh design of the disease. Perhaps we need take from MRI or CT scans the image, and probably we need different image acquisition in different times in a specific way that the clinician knows that with this data, probably you can extrapolate this data with machine learning. Though, in more specific way, because your answer really is probably the most that you can say. Imagine them that I give you 3 or 4 images after a surgical procedure in vessels with dynamics, with changing morphology. I give an image with mesh in the day 1, day 7, 1 month, and 3 months. And I would like to know what happens in 6 months. And I give you all the data related with imaging, with a mesh, and dynamics in different points in order to know the velocity, the stress conditions, all related with the energy power in each of the points of the mesh. Now, with machine learning and the infrastructure of parallel computing and so on, we'll be able with this data to see what happens in the later months or so, like something like this. With this answer to your answer, you can formulate some kind of simulation model, or we need more data?
Let me see. I give you an example on a different area that is directly answer this question. Back to the COVID-19. Doing predictions, there were a number of people, including some Nobel laureates, making predictions of the course of the epidemic based on curve fitting. You see how it's progressing, you see it's progressing more, you can do a very nice curve fitting and see what is going to happen. Obviously, that doesn't work because you are not taking into account all the other things that are influencing the process in a dramatic way. So you need other type of models that are not working very well, that are all the epidemiological models in which you try to define the different conditions and how they are progressing, because only curve fitting will not be enough for understanding a complex process. So you go to your images, time course, different conditions in different time points. If it is a continuous process and can be extrapolated on time, and you can do this with all the information, then I guess the model will work. As soon as it's a complex process with some disruptive things happening, you will be lost because then you don't have information about that. So I think that you can use the initial phase of training with this information to be in a better position to ask why this is not working, what are the things that are missing, that are not part of the information I have, and then go back to the experts and ask why this curve fitting or this extrapolation is not working, because I'm sure will not be working very likely. And if it's working, fantastic, but then likely will not be working, and say, what is the thing that we are missing? And what is the part of this process that is or external or emerging that cannot be accounted by a direct extrapolation? And I think this is the point in which this is the point to say that all these systems can only be developed in specific areas with the experts. There is no a general magic solution for everything. I guess it's okay.
There is no magic solution. That's the answer.
I have a question related to this topic, because as you said in the COVID, you could see that most of the models of sometimes the predictions fail. And I think it's, as you said, because there are some aspects or some items that you don't know, and later when the model is not working properly, you analyze it and said, okay, it was this that we don't taking care before. So maybe in the modeling on all the disease happen the same. You are very well predicting what has happened, but you are not so well to predicting the future. So we are always learning. And what do you think that, because before we talk about the importance of the data, of the quality of the data that you are beginning the model. So what are your strategy to begin, for example, a project to make models. How do you analyze the quality of your data?
Yeah, that's a very good question, and I don't think that there is any standard procedure to do that. There is nothing system. There is not a systematic to do that. Obviously, we are depending on quantity and quality of the data. We need quantities, and that's something we can say something more about. And then we need this data to be of quality. When we go to other areas, normally engineers are surprised by all problems, no? Because you go to talk to machines produce data that is very, very stable, and you go to meteorology or something like that, you get all this data that is very systematic and is always stable and the same quality, and you can associate the quality to the machines, and that's it. For us in biology or in medicine, it's nothing like that. The data is very variable, it's very, very patchy, and the quality is very heterogeneous. So we are used to these problems, and I think that anyone developing methods in this area, any type of methods, will be aware of the quality problems and will be very well prepared for dealing with data quality. So we are, I would say, we are better prepared to accept the difficulties of the data and prepare methods that will be as resistant as possible to the difficulties with the data. So, in a sense, what you try to do is to try to have the most possible robust approach, knowing that not all your data, even in the best of the cases, is going to be of high quality. We are very interested or fan of approaches that are based on progressive training, and you can give these two different names. I mean, you label some data and a small amount of data with high quality, you train your model, you know it's not enough, and you see that it's not going to extrapolate because it's not enough data, but then you are already labeling other data that is the one that is more likely to be okay because you score this high based on what you have already done with the initial data. So now you go and annotate a second round of data, again, small with quality, that is easier to annotate because it's the one that you have already predicted or is closer to your predictions from the first round. And you do this iteratively a number of times in a way that by labeling, training, predicting, labeling, training, predicting, you are progressing without entering in the full mass of data, acquiring by step knowledge based on high quality data, without entering a big campaign of annotating a lot of data that is very expensive and probably cannot be done in many cases. So this is one thing we do with respect to data quality, so taking these steps of training. And the other one that is very much related is using a lot of combining what we call gold data and silver data set. So you can have a gold standard that is annotated by humans and is high quality, and normally it's small, but then you can have big silver data set that are annotated by a number of different methods. And then the quality is not as good as the one of the human annotated, but it's good, is better than the rest because different methods are predicting this type of data or labeling this type of data as correct. So by combining these gold and silver standards, there are many methods that work in this combination. And that's how they, for example, in the tech mining, how many of the systems are trained by this combination of gold and silver standards. I wanted to say something else, and it's a question back to you. We are very interested in the problem of, because all what we are talking here is we are thinking in machine learning and big data, or modeling and big data. We need a lot of data for training a system. I showed you how much data we need to build a language model. This is fine, but when we go to medical problems, and that's a question back to you, we will find that in many cases there is no big data. We are talking about rare diseases or rare cancer. There is no big data. There is no more patients. That's it. That's what we have. So we are more and more thinking in small data problems. What is the machine learning applications for small data? And the full technology is very well developed for large data set, but not so much for a small data set. Small and deep. The cases we are working with are rare diseases. The number of cases is in the 100. But then for each one of these cases, you have a lot of whatever medical and genomic information. So it's deep, but shallow in the number of cases. Small number of cases, very deep. And I'm back to you. I think this is, I'm very enthusiastic about that because I think this is closer to medical reality than many of the big data applications.
Okay. It's funny, actually, you asked that just now, because pretty much that was the other side of the question I was about to make to you, which is, because most of the examples you've given from the very beginning are from molecular biology or molecular biomedicine, bioinformatics, omics sciences, etc., which, for which a supercomputer or high performance computing, it's like the natural environment. But I mean, in a previous presentation, I was, not today, yesterday, I was trying to convince people that many of the problems in medicine are small data problems in kind of day-to-day practice. And, but not exactly the way you mentioned, because I mean, you are mentioning few cases, high dimensional spaces. That's again, a very kind of traditional problem in genetics or omics in general. And we are finding that type of problem, for instance, when analyzing protein dynamics simulations. But also there is even the other problem, which is the one that I usually am faced with, which is few cases and not even high dimensional, which again requires another completely different strategy, because many of the most successful methods, well, do not work well in that sort of situation. And for us, it's a kind of ongoing problem, because in many real medical problems, I mean, it's very expensive or just extremely complicated to obtain. I know you are studying rare brain tumors. Well, I mean, there are the number of brain tumors that cases that you have, or rare diseases in general. I mean, usually you have small data sets, and maybe you don't even have too many variables. So, I mean, for those, we have to kind of work out what sort of techniques are the most reliable. And definitely you don't go for deep learning for that sort of settings. But the one you are mentioning, I mean, I have never worked with that one, but I know people who are exactly in the same kind of conundrum. I mean, they don't really know what would be the best approach from the machine learning viewpoint to address small data sets with high dimension, with very, or even extremely large dimensionality. I don't think there is actually, I mean, I wish I knew, I mean, because my answer is that I don't have a bloody idea. I mean, I know that people are working on the problem, but as far as I know, to the best of my knowledge, it's an unsolved problem. I mean, how to deal effectively. And I know lots of people trying to work with simulated data, to amplify, to augment the small number of cases we have. But to be honest, I'm not even sure that in many situations that's going to be reliable enough, or enough to generalize properly and extrapolate, for the medical problem itself.
We used to work with this kind of data. We have not so many patients. We have a lot of variables. And we think, I think that maybe it's the correlation with the clinical endpoint, that it's trying to make a correlation, but we use classical statistics in this approach. And later we have the problem that sometimes we use linear models for variables that maybe are not linear, and we have small data, and we don't know how to deal with this problem, because maybe we don't find any statistical significance correlation, but it's the problem that the errors that we have with this data. To say something to say about?
This microphone is not working.
Now, you hear me?
No, no.
Okay, this is a fantastic question, Alfonso. This is a fantastic question for both, for both sides. And in fact, I was going to make a similar question to this. Well, one of the main bottlenecks is the data we use, the number of data we have. And well, we don't work with big data. The definition of big data is not this. You use the technology big data in our environment. And then here, for the perspective of a clinician, when we use the classical statistics, the first point that we have considered also is to calculate the sample size of a sample. The sample size in order to say, if I have the result that there is no difference, really there is no difference. But if I don't calculate the sample size, there is no difference. I don't know if the sample size is enough to have this conclusion. That's the first point. Yeah. Right? Then, in this context, when I'm lucky and with a few patients I have a significant difference, fantastic. But if not, I have a problem. Then, in the second point, I have enough sample size, but for one or two aims. But if I want to create a multivariate study, I need a higher sample size depending on the variables I have to analyze in the multivariate study. And if I have some problem, the statistician can be creative in order to find some solution. And all we know that if we work with data a lot, sometimes we find results, but in artificial way. We know how it works. Then in this context, in artificial intelligence, probably is the same, because as Alfredo says, we can be creative, augmenting the size of the sample, creating mirror samples and so on, amplifying the sample size and so on. And we know that this works in some situations, but in others not. In others, we are lying with ourselves. Then, in this context, from a clinical point of view, there is only two solutions. One, that is use the technology as much as we can in order to get solutions, but we are in the risk of overfitting in our results, and we are going to have answers for a congress, a poster, or a publication, but not for life. Yeah. And the second point is, what about, and this is my question after the answer, is what about the data biobanks? In fact, in Europe, when you ask for a huge grant, they advise you better after you finish your work, get the data somewhere in order to put the whole community. This is quite good. And in any specialties, you can go to databases in the network, in huge hospitals and so on. This is typical in the United States, in order to get data to train your students and so on. Yeah. Then my open question to you and to Alfredo is, you have spoken about the different networks, a fantastic network, we are working, we are speaking. What about the data sharing process after or during different kind of research projects? Because all the data you have there in the supercomputing center or in your hospital or in my hospital, I personally think that we should, in some moment, perhaps at the finish of the project, to share this data in huge bank. Because in this context, the data that had been working previously in a huge project are going to be a fantastic data set prepared to keep working on other projects. Then, if we work in a systematic way, perhaps the answer to the lack of data is only to get more data in different projects. What do you think about this? Or you have some experience in this arena?
Sure. Let's all these. First of all, I'm very happy to hear that I'm not completely wrong in thinking that the small data problems are very proper in medicine. No. For you looks very obvious, but I'm not a medical doctor, so I see this from the other side. So I'm happy to see that I'm not completely wrong in this. You have to already mention all the problems and all the tools. We are very interested in this problem of the generation of artificial data. All the embeddings used to extrapolate the space is a very promising technology. But we know the problem of working with artificial data and expanding and we are back to this problem of expanding. We can expand known conditions, but we may not be able to enter into a region that has not been seen before. So the expansion has a limit, and we expand on the known, but we cannot expand in the unknowns, and that's its obvious limitation of working with synthetic data. Still, this technology is evolving very fast, and the results are becoming really interesting. The other alternative, thinking on the machine learning side, obviously, is all the transfer learning potential. Training on similar data, trying to surround your few cases with other similar data sets of problems, and learning from these other cases and trying to transfer this to your case. Again, there is no magic, but also the examples on this type of applications are becoming really, really powerful. So that I would say there are two other things that, at least in our case, these are the two things that we are interested in exploring, and the two then are evolving very fast and looks very promising. And we will see what is the level. Obviously, it's probably a small data, a small number of cases with a lot of data. Then there are many more things that can be done. If it's a small data with very few variables, then obviously it's far less of what you can do. That's I guess it's obvious. So that's my take on the small data. And then if maybe you want to say something to that, we can go to the data banks. That is another completely different and interesting area. Maybe you want to say something on the small data set side. I didn't hear your talk, by the way, so we should talk about that.
No, I mean, in fact, no, it was not about the small data sets, but it was about already leading towards this idea of biodata banks, whatever we want to call them, because that's something that has come up in some of the previous discussion before you joined, which is in the end that, doesn't really matter whether we are talking about machine learning or artificial intelligence. The bottleneck is in the data themselves, and how can we access them, and problems of anonymization, pseudonymization, privacy, GDPR, whatever. I always, whenever we talk about this thing, I always remember that the first time I was kind of aware of this sort of situation was, the first time I started a project with in neuro-oncology with brain tumors and stuff. And in my first meeting with the guys who were in charge of the data, it was part of a European project. And they were so excited because they said, we have the biggest database of brain tumors. We have 14 types of brain tumors in here. Well, did sound exciting. Well, actually, what they had was like 300-400 tumors of 14 different classes. Okay, and it was not just that. The smallness. For them it was huge as the ocean. It was not just the smallness of it from the, let's say, data science machine learning point of view. It was that, they explained, and this is when I realized the problem. They had spent a year without fully solving it, the problem that part of their data came from General Electric machines, from magnetic resonance machines. Part of them came from General Electric machines, part of them came from Siemens machines. And formats were proprietary, and they were a nightmare to use together because there was no way to make them homogeneous. And they spent a full year of the European project just trying to make those 200 plus 200, okay, and make it 400. And that was the hugeness of it all. So, if you think about like large scale biodata banks as the solution, there are so many barriers in the middle until we get to something that can be used to make a small thing big, so to say, and then use machine learning by numbers. Most of the barriers don't seem to me like, this example is a technological barrier, but most of the barriers are political, almost administrative. They have to do with legislation, with norm, until we get, to get something that is an international data bank. with data from patients, from real human patients, up to a multi-center international scale. I mean, the barriers to me seem so far unsurmountable unless someone from the top makes a decision to, streamline the process of creating these data banks and removing all the potential barriers in the middle. But that seems even a more far-fetched idea to me than, for instance, the digital twin you mentioned before.
So, I mean, this is obviously as you already say, is the key topic. The key topic is data access. The rest, we can do more or less, but if there is no data, we cannot do anything else. Other areas, biology, in biology, have already solved this problem to a very large extent. 30 years ago, the protein structures were kept by the crystallographers because they were afraid that someone else was going to publish before them, something. Now the structures are put in the PDB and nobody questioned that. So the thing gets more complicated obviously with the personal data, but for the genomic data, we have already built enough infrastructure to really not, I wouldn't say solve the problem, but to know how to solve the problem. And there are these European Genome Phenome Archive. The database contains genomic information as a way of working in federation, in a way that you can still keep the data in the different sites. The larger the site, the better, but you can keep it in different sites and operate the information this way. All the European projects, countries that are developing personalized medicine projects are based on this idea of federated EGA repositories. And the full, the 1 million genome project European effort is also based on this idea of federated EGA genomic data. I'm not saying that we have solved the problem, but at least we know what is the way in which the problem can be solved. The real problem is the problem of the medical information. The electronic health records, more than the images, because for the images, there is also more repositories and easier ways of sharing the information. First of all, the information is far more complex. As you know, the health system, the hospitals themselves have problem dealing with their own data without thinking in extrapolating or something. Even more with sharing the data. And as you say, there are problems at all the levels. There is a problem of perception. The data belong to the health system, and the health systems are now convinced that this has a value, and they want to be part of the chain of value. If something is developed on the data, they want to be part of the development for reasons that are understandable. Then there are political problems. Do I share with these people or I don't share with these people something? And then the political problems add up to the legislation type of problems. I think that essentially the GDPR has been interpreted in a way that is completely contrary to what was intended for. The GDPR was created to facilitate the use of omic data and health data for research. And in practice, what it is used for is to prevent the use of the data, what is completely the opposite of what this should be. Now there are big initiatives to try to make data accessible, particularly medical data accessible. The creation of the European health area is, the main intention is to be able to share this data in a federated way. And there is the political movement to do that. You see, the political movement is translated into something practical, and the countries are really taking this into account. It is important not to forget that it's not a problem of countries, it's a problem of regions. In Spain, there are 17 different regions, each one of them with capacity to decide on their medical data. In Italy, there are 23, if I'm not mistaken. So in Germany, there are 17 or 16 or something, that they are also pretty independent But even in smaller countries, for Denmark, with a lot of money and a lot of different attitude to really public data, and still they have a lot of problems putting together the data. So we see, I think this is essential. If we don't solve the problem of the access to the information, the rest is impossible, and particularly the access to the medical information. We are trusting in the idea of federated systems, being able to recover data from different systems to put it together to create cohorts and to create studies, and federated learning. There is not a demonstration that the federated learning systems are really going to be as effective as we want them to be. And we should be careful about that. And I was just hearing before this meeting about a project doing federated learning on drugs. And the results so far are that the federated systems are not better than the systems in the companies, pharma companies. So that's yes, we need the data. There are problems. There are a lot of discussion points. Now this problem has become really on the spotlight. There is a goodwill from the Commission, I guess, from the countries to solve the problem. We see if they are able to do it or not.
Karina Giver from the UPC is now online. She's not?
No, they say
Oh.
No, she was supposed to have entered soon, but she hasn't just yet.
Ah, okay. So we will wait for her for make.
Well, no. Otherwise, I mean, we can conclude the.
Yes. Okay. Last question.
I would like to make a practical question. Here have a pleasure to have you among ourselves to enjoy this fantastic table. And as we are creating the perfect storm of fantastic, we know that we have to have access to huge data of high quality, good pre-processing data, and after to create the correct question to solve a problem with machine learning, imagine that we have all different steps. We have passed through all these different steps, and I have all the data, and I create a predictive model by sitting simulation, and I would like to go to the Barcelona Supercomputing Center. What are the different steps that I have to go through in order to be evaluated and have the possibility to work in the supercomputing using the possibility of your infrastructure? This is an open question for the people that can.
Yeah, thanks for the question, because this is very important for us. So first of all, the Barcelona Supercomputing Center, Mare Nostrum, is a public infrastructure, so it's to be used by people. Most of the time is used by people that are not at the BSc. So we are part of a network. It's called the Spanish Research RES, the Red Española de Supercomputación, Spanish Supercomputing Network, and we are part of an European network that is called PRACE, the European Supercomputing Network. So for the two of them, what you do is to apply with a project. So you have your project, you want to do your calculations or something, you describe what you want to do and what you need in terms of computation. If you don't exactly know what you need in terms of computation, you can ask for a training period to calibrate what you need. And then you get time in one of the computers, minus to know one of the other computers of the rest, or you really want more time and you need something even bigger, you apply for PRACE, that is the European network, and then you get time in any of the computers in Germany, France, Italy, or Spain that are part of PRACE in the current configuration. PRACE projects are more difficult to get, but then you get millions of hours. REST projects are easier to get, and then you get enough time for most projects. So that's the standard way of getting into the something. And then there is a help desk, and they help you to install the software and to do your runs and all that. At the same time, REST has started, and the last call was a few weeks ago, a project for data storage for projects. This is providing a space for storing your data for the next 3 or 5 years. So you have the project, again, same thing, you apply, there will be a future call, you apply, you have your project, you are getting this type of data, and you want to store this data. You obviously it's a data that is not just to archive the data, it's data that you are planning to use or being used by others. And the ideal configuration is that this data will be stored close to a computing center when you will then ask for project to use your data or this data, whatever is yours or from someone else. So there are these 3 open windows to ask for: European projects, very large scale computing, European project, Spanish project, high performance, but not doesn't need to be so that that many millions of hours of computing, and then the possibility of asking for time for storage, and then you have to find. These are the obvious ones. Then if there are special projects, there may be other solutions. But in general, these are the open windows for projects.
Fantastic, Alfonso. I hope sometime have the opportunity to visit your center.
You are all of you are most welcome to visit. We have thousands of visitors, including from schools to meetings to people to anything. There will be you can just say there was, and there will be again a place to apply for visits. We are now moving to a new building. So we will keep the chapter with the computer, but the full center is moving to a new building, and there will be a much larger computing center to host the new Mare Nostrum. So the visit will be not only to a chapel, but the new installation that is, there will be the contrast between the new one that is very modern and flashy and the old one in the chapel. So there will be a full visit organized for that, and you are most welcome to visit anytime. I see Karina wanting to say something.
Sorry, now can you hear me?
Yes, yes.
Thank you very much. Thank you. Nice to meet you, Alfonso. It's always such a pleasure to listen for you, and you always are doing such nice research. And I strongly recommend everybody to try to make this visit to the Mare Nostrum, because if I'm not wrong, it is the old one is the single one in the world that lives inside the chapel, right?
We won there was a competition, and we won the first prize to a nicer supercomputer in the world.
It's very nice. Well, I just want to share with you a thinking that always worries me a lot, because we are moving towards a scenario in which big data becomes an intensive nucleus of much of the research, but not only in research, but also in business, no? And I'm worried always about the ecological print of that thing. So I would like to listen to your thinkings about in the mean future. You think that we will really continue staying on intensifying the big data applications everywhere, or do you think we have to concentrate the efforts on the big data in some particular kind of problems or particular areas and try to move towards some kind of saving energy and saving data in favor of these sustainability issues under some principles, let's say?
No, very good, very good and very proper question. So I didn't have the time to it was in one of my slides, the comparison of how much energy training the natural language processing system cost, and how much and the equivalence in trips across the Atlantic. And it's very scary. Training one of these systems is an ecological disaster, essentially. So we have to be very careful about what we are doing. So there are a number of things that are going in parallel. First of all, for us, paying the electricity is a big issue. We pay a lot in electricity every month. So for practical reasons and for other more moral reasons, and because all the movement is going in this direction, the machines are struggling to be not only very powerful, but being very energy efficient. And then the next machine will be almost 20 times more powerful, but in terms of energy consumption, probably will not be more than 2-3 times more consuming than Marina's. And everybody's thinking in the cooling system, the something, because we spend a lot of, essentially the good part of the bill is on the cooling system, and the cooling system has improved a lot. Indeed, by the way, the cooling systems are controlled by the artificial intelligence too, so it's very redundant. The second one is so the design. This is the design of the full system, also the design of the proper design of the CPUs, even a more basic level. Far from my area, but I hear from my boss, from Matteo, is also very much energy aware. And then the algorithm. There is a lot of thing about green algorithm. I'm not sure if the algorithms are going to be green themselves, but the use of the high-performance computing has to be more rational. And I give you one example of something we are working, like many other people in the world, is we launch these simulations, and we explore a lot of parameter space. But we know from the beginning, you see how the things are evolving, and then you know very soon that this simulation is going to end up somewhere that you already know. And there is no really need to continue this because you know it's going to, first this cell is going to die, so I already know that. So the effort is to develop methods to be able to catch these trajectories that are going to end up somewhere that you don't need to go, stop it, and dedicate the CPUs to do something else. So the interweave between machine learning and simulations is very much going into the direction not only having better algorithms that will be more efficient, something, but also catching the simulations or organizing the exploration of the parameter space and the follow-up of the simulations in a way that they can save cycles. The experiments we are doing is amazing because you may predicting the course, imagine some machine learning predicting how this simulation is going to end up. So if I can predict it, I don't need to calculate it, so I'm saving all this energy. You may end up saving half of your simulation by applying machine learning. So I think that there is everybody is very conscious of the problem, the scientists, but also the regulatory bodies. And I think we are going to see progress in this area. After saying that, we do all this progress, and then people are spending far more in calculating, in mining coins. That is, from my point of view, a less interesting thing to do than exploring tumors or diseases.
Absolutely. Thank you very much, Alfonso. Without doubt, science has been making improvements thanks to big data in the last years in an incredible way. So there's no doubt about that. And I think, you see that the situation is basically on technology, on machines, on how machines are efficient, and also on algorithms. I think also on designing data. We should also think about that. But thank you very much.
Thank you.
It's the end of this Science for Dialysis. Thanks again for all the people who has been here, for the speakers, for their nice and inspiring talks. Josep, Alfonso, the co-chairman, Alfredo, Karina also, and the people from audiovisual, from Hospital de Belviche, Xavier, Isabel, and all the assistants that have been connecting with us. So we are waiting for you for the next Science for Dialysis. It will be number 5. So we have to think about the topics that we try to talk about. Thank you very much. And Alfredo, something?
No, thank you so much. It's been,
reduce this edition to this virtual form. We aim to, make it bigger and resounding And hopefully this, even though it's been a live stream, hopefully the recording will be available on YouTube as well. Anyhow, and by the way, just mentioning that it's a pity that Karina joined us late, but I'm really glad she made it in the end. And I want to mention only that she's, by the way, from very recent time, the director of the EDI Research Center. So thank you so much, Karina, for joining us.
Thank you very much. I was ensuring a previous meeting just to try to arrive, to have the opportunity to connect. Yes. Thanks for organizing this session.
You're welcome. And thank you, Alfonso, for joining us from Madrid, and to Josep from live here from the studio, from which we wish you a very nice day. Bye now.
Thank you. Bye-bye.
Thank you very much. Thank you. A pleasure.